Waiting for Twitch to catch up as usual. Okay, anytime now. There we go. Okay. Hello, everyone. Welcome to an unplanned stream this evening. I usually stream on Tuesdays and Thursdays, but this evening I had nothing else planned. I really wanted to make some progress on the thing we started yesterday. So here's an unplanned stream with no camera and just to make some progress. So, yesterday we started the work on the lowering into the IR. And we started defining the IR and we started implemented this research paper right here for an algorithm to transform into a static single assignment IR from an AST. And I made a lot of progress, but I got stuck towards the end because I was not sure how to model the recursion over blocks. See, my issue was this. I was treating this as a recursive problem. We stack different scopes every time we encounter a nested block within a block. But the problem is, we might not be able to create a block when we come back from the recursion because a sequence of instructions might be segmented into several blocks because the body of a while loop might contain an if, for instance, that creates several different blocks. And I wasn't sure how to approach this. And I started doing some complicated nonsense here with the lowering monad that ended up being quite complicated and just not correct. So I stopped for yesterday evening, and of course, as is always the case, I found the solution to my problem within an hour of stopping for the evening. So unplanned stream this evening just to try to clean up the things we started yesterday, just to try to make some progress on this and clean up a few things. So first, we are not going to need the monad lowering anymore. That's not going to be a thing. Run lowering can stay. The block M monad that adds a new state is no longer required. The block state will not keep existing in the same shape. So I can move that down. Run block is therefore no longer going to be required either. And we're going to clean a few things. So our lowering monad, in which we do the algorithm in question, in which we do the operation of lowering from the AST into the AR, for now, I might actually want to do that as part of today. I might not do that now. This will become extremely similar to the one we have for the analysis, which, if you remember, looks like this. It is a read-write state monad. The read is the analysis info, the state is the analysis state, and the write is the list of diagnostics, errors, and warnings we found as part of the analysis phase. For now, here we have reader and state. We don't have the writer. I thought naively that there would be no need for diagnostics at this point in the compiler because we're done with the analysis. We've already not done all of the type checking and the name checking and all of that. And in theory, there shouldn't be any errors in the code coming from the user. I was wrong about that. I've thought about a few things, a few cases where we want to emit errors, where we want the compilation to fail, that would arise from the process of lowering to the AR. And this comes from the fact that as part of this process, we are doing control flow analysis. So there are a few things that we can identify that are not name checking or type checking things that will require emitting diagnosis, warnings, or even errors. One example of warning would be unreachable code. Here's an instruction that causes some branching, but that cannot be reached. For instance, we have an if-else block in which both the branches contain a return and something after the if-else. Well, that thing is unreachable, and we can only detect that by doing control flow analysis. Or a function doesn't have a return in all branches, meaning there are blocks that end with no return, despite the fact that it does not return unit. Those things will be detected through control flow analysis, which will be part of this phase. So at some point, we will have to change this monad to also have a way to report diagnostics. I'm not going to do that now, but that's something we're going to have to do. Now, the interface is the thing that's coming from the previous phase. So it's the result of doing the analysis of a module. That doesn't change. It is the reader part. So it's the thing that is accessible throughout the operation, but doesn't change as the operation progresses. The state is the interesting part. Some of the state will be hidden within this module and will not be accessible to the rest of the code. For instance, the fact that the next label and the next register are ints is an implementation detail that will be not be exposed to the rest of the code. And instead, what we expose are things such as create label, create register that do increment the value in the state and return a new label or a new register. But that is the interface we provide to the rest of the code. Now, what I want to change is I had this idea of the block state of like, oh, we have the state of a block as it is being constructed, and we can stack that on top of the thing because we're doing one block at a time. This was not necessarily a bad idea, but again, since we still have some amount of recursion because we have to handle nested things within nested things, a while loop inside a for loop inside an if block, that kind of stuff, we will need to have some kind of recursion. But within a set of instructions, again, we might end up creating several blocks. So this approach doesn't work. So what I'm going to do instead is I am going to maintain what I'm going to call a scope, which is going to be a list, which is going to be empty by default, but when we are at the top level, which describes the current inner scope in which we are. And I'm going to call that a block scope. And the block scope will be something I'm going to change here. The label, the instructions, all of that is irrelevant. This will be stored in the block, which is here. What a block scope will contain is three things. Fall through, I think, would be a good name. Which I guess should be a label. Yep, something like this. And those are the labels of the blocks that would be the one to jump to in case we fall through, we have reached the end of the instructions in this block. And in an if block, for instance, this would be the block after the if then else. In a loop, this would be back to the block that contains the loop condition. Continue and break are optional because we might not be in a loop, and they are the label of the block to which we jump for a continue or a break for the innermost loop in which we are. And I think this approach is going to be enough, and we're just going to do something a bit stateful. Rather than creating blocks and inserting them into the hash map is part of the set. We'll be modifying the blocks in the hash map as we go, basically. Which is going to be a bit less performance efficient, but at this point, performance is not something we have really cared much about. So we will do performance analysis and improvement at a later stage. So now I just need to change this state to be so potential sealed blocks, and I'm missing here the scope, which by default is just an empty list, indicating that we are at the top level. Make label, make register, I'm not going to change. Those can stay the way they are. Current label doesn't... Now, yeah, those things, however, are not... Some of those are actually going to remain the same. This goes away. Because I don't want to expose all of this to the rest of the code. I want to expose only a few functions that deal with this... with that state without actually exposing all of the details. For instance, I could make, rather than exposing the sealed lens, like I do at the moment, I think. Yep, I am tempted to instead expose is sealed and seal that actually modify the state accordingly. And let's do that. So is sealed will be something that takes a label and checks within the context if that value is sealed, and is sealed, given a label, is just uses of lookup, actually member, I think. Let me check. Sorry for the high change in contrast. Is there a member function? There is. Perfect. Oh, actually, this is a hash set, so that is even what I want. It is just member of the hash set, so I can rewrite it 0.3 like this, I think. And of course, I want to do that in the sealed set. There we go. And this is not in any monad, it is in the lowering monad. Likewise here, we no longer have a stack of monad per block, therefore we can go back to just specialize. There we go. And to seal something will be to do a modify given some label, and I might make it 0.3 if that makes sense. ls sealed, the state, the lens within my state will be modified in the state by applying the function insert of the label. I could make it 0.3, but that would be less readable, so I'm not going to do that. And in fact, here, likewise, I think it's more readable as being... And let me just quickly check something, which is that I'm using the member function correctly. Member is indeed key then hash set. So member label is a partial function that takes a hash set, returns a boolean, and I'm using uses to use this lens on the state and apply this function on it. Okay. So now I don't need to expose the sealed hash set to the rest of the code. I am only exposing those two functions. It's a bit safer. Now, those current things do not make sense. However, what I can do instead is I can change those. Current label doesn't make sense. What I want to do is basically current scope, which is going to be something that in my lowering monad gives me one of those block scopes. But it gives me a maybe block scope, because if we are at the top level, there will not be a block scope to return. So this will be... that lens is going to be something. It's going to be a use, and the lens we are going to apply is going to be the scope. I don't remember. Is it like an add 0 or something like this? Would that work? Or is it like maybe an underscore head or something like this? I never remember. I do have lens imported. We'll see. We'll see if lens isn't happy about this. Or head underscore. I would want something. Let's see if Google knows about lens. I would want something which would have more or less the shape given a lens. It would be a traversal from list of A to maybe A? Nah, okay. Let's have a look at the documentation. It wouldn't be getter, I think. Would it be? Well, I think it would be in the traversals. Maybe at? I think at 0 would probably work. But at 0 feels inelegant compared to something like head or something. Would that be in the fold? No, okay. Oh, something I could have checked with Google actually. If I look for head underscore, and there's no lens here, and underscore head, I was convinced there was one like this. Ah, lens, there we go. There is in control lens combinator. There we go. Reading and writing to the head of a non-empty container, but I can use it with, okay. Actually, something I need to check in the getter thing of lenses. Is there a way to do an equivalent for use, but that gives me something that returns a maybe? No, okay. That's fine. Okay, so maybe a at 0 or something is the easiest. We will see what the compiler says when I try to compile this. Now, okay, so that gives me the maybe scope of the current scope. Now I can check a few more. I can actually make a few more direct function. I can make current fall through, which is going to be the same thing, which is going to be basically current scope on which I apply it's a double F map actually. Because I'm MF mapping within the lowering M and within the maybe. Oh, actually, it's more complicated than that. So let's write it down. I get the scope from which is from the current scope, which is a maybe scope, and I return that scope on which I will do a monadic bind. So that this is a maybe value. I do a monadic bind, so it takes a function that takes the value inside the maybe, returns another maybe, which would be this. Oh, fall through doesn't actually take. Okay, so there's no need to do that. But for the others, I will need to do that. So this is gonna be of the scope. So it's just an F map, which means I could rewrite this as a double F map. But since I'm going to do this for the others, I'm going to keep the same structure so that the structure is obvious. This is a maybe label. Maybe label for the current break, which is here that we're going to do a monadic bind in the maybe monad with the BS break, and likewise for the continue. Okay, there we go. Okay, so this is accessing the current scope. Are there a few other things that I would like to... I think register lookup is complicated enough that maybe I want to... Like, I'm trying to see... Ideally, I'd like to hide as many of the lenses as possible and use functions that have like a very specific purpose rather than letting the calling code modify the state at will. The idea being, if I can restrict as much as possible how the state is being used, I can guarantee that it is used correctly in the rest of the code. I can reduce the risk of misuse. Like, for instance, if I don't expose the whole hash set of sealed blocks, I can guarantee that there is no code in the rest of the project that might like erase it by mistake as part of the process, mark a sealed block as unsealed, because the only functions available to the rest of the code are is sealed and seal, basically. There's no unseal. So I'm trying to see what else I can do along those lines. And I think I need to do for the scope, I have read access to the things of the scope, but I need to be able to also do something that changes the scope. And this would be an operation that transforms recursively the scope underneath. So it would be something along those lines. This is where error handling is going to be complicated, but that's a problem for later. So with scope, I suppose, which is going to be, do I take a full block scope as an argument? Or do I instead create a with scope function for basic scopes and for loops? With inner scope only takes the label that is the fall through, as in when that block is over, where do we go from there? And then takes an action in the lowering monad and returns an action in the lowering monad. This is the action that we wrap with the stuff that manipulates the scope. So this is going to be used, for instance, for an if or an else, something like this, that does not modify, that is not a new loop, basically. And the only thing that we care about is where do we go when this thing ends, basically. So that is going to be I will want to get the current scope, if any. There might not be one. The new scope is going to be a block scope in which we have the fall through. Actually, it's going to be... actually, no, I come to that. It's going to be... Which order are they? They're continue and then break. It is the continue of the previous one. And it is the break of the previous one. So if we are in an if within a loop, the continue and the break still go to the same place. So within a loop, if you do if something break, the break we go to, the destination of the break is the same as the one from the loop. But if you put a loop within the loop, the break is only applied to the inner loop. That is the logic that we apply here. So that is our new scope. We modify the current scope, which is the lowering state scope. We modify that list by appending the new scope at the beginning of our linked list. Then we collect the result from the action. This is the action that was given as an argument. That's going to be the inner thing of the recursion. And after this, we modify the scope again by removing the first scope, and we can return the result. And so that's inner scope and with inner loop. I guess with loop is enough, I think. And this, however, requires the fall through and the continue and the break. And here we don't need to modify the current scope. This is always going to be a new scope. We override everything. So it is just the continue, just the break. We modify the scope to contain the state to contain the new scope. We execute the action, we pop the scope, and we return the result. Okay? Next, what do we do? So that doesn't make sense anymore. This is something that we can probably get rid of. That is, I think, just the old version of those. Okay. And I guess the last thing we need, those are things... I'm not sure exactly which ones we need, so I'm just going to do them as we go, which are going to be modifying the current block, basically. So all of those are going to need the label of the block that we're modifying. And they're all going to be basically a lens in the state. So this is going to be in the state. It's going to be at label modified dot something dot instructions. What's the definition of a block that's in the EIR? Block instruction, block instructions, block argument. Block instructions modified to add that instruction at the end of the linked list. So that's very ugly. We will have to change this for performance at some point. But basically the same thing here. And this block at label, the block registers, block arguments. We modify that list by appending the register at the end of the list. Okay, that should give us a better framework to work with. We can go back to here. So now I guess this has become wrong, I suppose. This has become wrong. This will have to become instead when there are temporary thing. Okay, so that's... I can do that. This is the LS potential. And here this becomes instead seal the label, because we have made this seal function here somewhere. Wrong one here. Seal, there we go. Oh, except... There we go. Now. So everything here is going to change. So filling a block, I think, becomes... I think this function cannot stay the same. I think it is completely wrong now. However, the lower function should change very little. So this should be... So make label for the start label, that makes sense. Seal block the start label, that's fine. Fill block start label the fun body, that's correct. That should register everything, and at the end... Okay, yeah, I think this function remains exactly the same. So fill block is the one we're going to have to change. It doesn't take the continue and break. That doesn't make sense anymore. Run block doesn't exist. It doesn't make sense anymore. I guess, do we actually need anything but just do we need anything but a function which is process the next argument? I think we don't actually. I don't think there's a need to care about the no, I think we don't need to. Okay, so let's rewrite this entirely. This will be step in block, I suppose, rather. And this will be a function that, given the list of instructions that we have as an argument, which actually is required here in the arguments, it is a list of statement resolved, I believe. Oh, I think I have a... Oh, it is the block resolved. I'm an idiot. It's already there. I think the only thing we care about here is basically like, is there an instruction for us to consume? So I can either yeah, I'm gonna just do this as a case. So in the case where we have no instruction to deal with, then what we do will depend on the current fall through value. So let's get the next label, which is going to be current fall through. If that gives us nothing, that means we are at the top level. This is where we need to check by looking at the context. Let's do this properly. If we have, can I rewrite this actually? Like so, bind in a case. In the case where we do have a fall through label, that's the best case. Okay, we're done with the instructions of this block, but we are not at the top level. We are in a loop. We are in an if. We know where to go next. So we know that the current block needs to be changed to point at the end with a terminator to the next label. So we can do that. I'm gonna actually add a helper function for this. Set terminator for a given label and a given terminator. And this is just gonna be for the blocks, add that label, and it's gonna be the block terminator. And it's just gonna be set to the term. So in this case, we have no more instructions in the current block. There is a label to which we can jump. So basically, if we go back to this, we know that there is like another block to which we can jump that is identified uniquely by a label, which means we can just say that the terminator of that current block is jump to the next label. And we need to register the parent. So I'm going to add another function for this, which means I'm going to be able to hide yet another Yeah, I'm gonna be able to hide yet another lens from the exports of this, I think. So let's do that. I have here for the sealed thing, uh, parent of a label will give me a list of label in the monad, and parents of a label uses the parents with a lookup of the label, and register parent would be, do I do key value? I think it makes the most sense. So it would be first the label and second its parent, and that becomes ls parents is modified by applying insert with concatenation Oh, lookup will give me a maybe. It's going to give me a maybe list, which means I can do a fold of that to transform maybe of a list into an empty list if there is no registered value. And here this is going to be label parent. There we go. There's one more thing. I think here for the label, I'm setting the parent. I don't think that's required. So I can just do that, because now that I have a lens for the parents that does the fold properly and then insert with, there is no longer any need to register parents ahead of time. Okay. I'll have to change my exports, actually. This is wrong now. The lowering state I probably don't want to expose. Block scope I don't want to expose either. But I will need... So for now, we're only exposing registers, potential, and blocks. Yeah. Some of them might be able... might be able to remove some of them, but it's fine for now to keep them like this. So make register is sealed and seal. Parents and register parent. And then current scope, current fall through, current continue, current break. And finally, within a scope with loop and the append. Append instructions, append argument, set terminator. Let's go back to the lowering process. We are in the case where we reach the end of the instructions of a block of statements. We look at the current fall through to know where we go to next. If there is one, that means we are in some case of inner scope or in a loop or something like this. That's perfect. We know that at the end of the block, we jump unconditionally to that next label. And that also means that the current block is a parent of the next label. Okay, and that should be everything we need to do in this case. In the nothing case, that means we are at the top level of the function and we have reached the end. And if we have reached the end, it means we did not detect. Oh, actually, maybe I will want to fix that. Okay, let me explain out loud what I'm thinking. Here, what I was trying to say is basically, okay, we've reached the end of the instructions at the top level of the function, so we are at the end of the function. We must check that the type of the function is like returns unit. It doesn't return anything because it means we did not encounter a return statement. However, for that to be true, for like to be able to guarantee that we reach this place if there was nothing to terminate before, it means that we must always do something else first. We must check that the current block in which we are has parents. If it has none, it means that we try to process something that is unreachable. There is no point, there is no, like, we will never be in a situation where we try to process a block that has no parents. It might not have all of them, in which case it might not be sealed, but it will have always at least one of them. So we only perform all of this when there are some parents. And I guess I'm going to introduce a new function for this. Is reachable is a function that, given a label, gives me a boolean. And is reachable is using a lens on the parents. What we do is we do a lookup of the label, and the result we do a fold to get a list, and then we do a null to check whether that list is empty, and we do a not because we want true if it's not empty and false if it is empty. Okay, I could even, nah, it's fine like this. Okay, so when m is reachable current, oh, I need to add it to the export list here. So when it is reachable, then we can do a case of the instructions. There's no point in handling the case where the current block is unreachable, and it's fine for something to be unreachable, especially if it's empty. Okay. So here we are back to this. There is no longer, we are in a block that is reachable. We can reach this place, but there is no instruction to process. And if we have a fall through, that's fine. We just say that the current label jumps to this next label and we register the parent. Otherwise, here, this would be, this is going to be a return nothing. So a return of unit because we ended up at the end. However, here is where to do emit error if function doesn't return unit. We've already done, as part of the type checking, the check that any return statement contains the correct value, but we did not do the control flow analysis as part of the analysis. So This will be done as part of this phase. So we will need to emit diagnostics here. Okay, so that's handled. Now we need to handle the case of there is some instruction, or rather some statement, and a bunch of statements. And here, another switch on what kind of statement we are facing. Which I suppose will be... Yeah, all of this is now moot. It's going to be a lot easier, so I think I can just delete all of this. And I can keep that, even though it's going to have to be changed. Okay, so let's go back to what we had. We do encounter a continue statement. A continue statement means the current set of instructions will jump unconditionally. We are at the end of the current block. The instructions that come after in this block will be ignored. So emit warning, unreachable code, if there are instructions after the continue in this block. Okay. And here, so here, yes, this is almost correct. Except now I have, is it current continue? Yes, it is current continue. So I look at where we're supposed to jump on a continue instruction. If I get nothing, this means that I am not in a loop. I am at the top level, or in an if at the top level, I am not in a loop. We have tested that all the continue and return statements were in a loop as part of the analysis, which means here, if that happens, that's just flat out an error. I guess this is a bit of a duplicated test, and I could remove that as part of the analysis, as in no need to keep track of are we in a loop or not. A continue statement is a continue statement, a break statement is a break statement. And here, rather than having an ICE, having something that reports an error to the user, which means this path of the code would be exercised. Maybe I'll leave the to-do for this. Okay. And then, okay, we are in the context of some kind of loop. We found a continue at some point in a set of instructions within that thing. The current block will end. Set terminator of the current block as being jump to the next label. And set parent of the next label, the current. The exact same thing as this, to the point where I'm kind of wondering if I should make something that combines both of those, but not yet. A break statement will be very, very similar, to the point I'm going to copy all of this. We found a break statement. If there are statements afterwards, they will be ignored, they are unreachable. We will emit a warning. If there is no break label at the moment in the state, that means we are at the top level or within like an if, nested ifs within the top level, but not in a loop. That is an error, which for now, since we've already checked those, is impossible and is an internal compiler error. But we might want to just not do the check as part of the analysis and just report an error there to the user. Then we set the terminator of the current block as being just a jump to the next label, and we label that the next label is reachable from the current one. Okay, a return statement then. We will have... we will need something called, like, either called lower expression or something like this, would like process expression, something like that, that will actually do the job of expanding a expression into a set of instructions for the AR, which is going to be the bulk of the work, which we will do later. Doesn't exist yet. And when we encounter this, so we have to process the expression, but then all of this becomes extremely similar. If there are statements after the current one, then emit a warning for unreachable code. And no, I don't have to look up for a next label because we are doing a return. So I suppose this is a traverse because type expression will be a maybe. And it's probably going to be a traverse with this because I don't actually care about the result. And so, no, this will not be. This will give me the register. This will give me the name of the register that is used to contain the result of this expression. And as a result, we set the terminator for the current as being return of that register, which might be nothing in the case of a function that doesn't return anything, returns a unit, when there is nothing there. And set parent doesn't make sense either, so that's what it is. Okay. Perfect. So that's a bunch of progress compared to yesterday evening. Now, before I tackle the rest of the statements, I am going to try to see if this compiles. And of course it won't, but let's fix that. Make lenses. That's because I need language template Haskell. That is missing. Oh, if I haven't tried to compile with the lenses, it's been a while since I've tried to compile. Deriving show because block scope doesn't have show. Current block state no longer exists. This is called block scope. Yes, this seal doesn't return anything. Okay. Likewise here, this operation register returns a unit. It doesn't return anything else. At label. Okay, so let's have a look. I always get confused by some of the lenses stuff. I will check that. We are using a setter. Let's have a look. Specifically here, we're using this one. Okay, so this requires something that is a setter. Map of a target of a lens or all of the target of a setter or traversal in harmonic state. Okay. So anything that is a setter or traversal will work. And I think at is what I want. It gives me a lens. It doesn't... Oh, read, write, or delete. Interesting. Okay, so why doesn't this work then? Because some of the examples suggest that this should work. Oh, I know what I'm doing wrong. Okay, so what I should do instead is rather than doing this, I should say I am modifying the blocks, and how I'm modifying them is by applying a function, and that function will be the result of doing at label block instructions set with this, something like this. Except I want this, something like that will be correct, I think. Lenses are magical. Something like that. Okay, so not exactly. Which means I will need one of those operations with, so I will need this one here. And for the modification ones, let's go back to look at setter. Is there? There is no modification. Oh, that's annoying. Oh, there is. But there's no. There is something to set, but there isn't something to modify conditionally. That is. Hmm. I guess if there was a way to have a default, I guess this might be the trick. I know that if something is a monoid and there is a default value, then some of the lenses that return maybe stuff are able to just always return a value by doing the insert, including some of the magic in at. Which means I think the key here is. Oh, that's gonna be ugly. I don't like doing that, but let's see if it works. And if it doesn't, then we're just not gonna do that. Yeah, I don't like doing that. I was gonna say if I make this a monoid and therefore there is an MMT definition for block, then I can always create a block by default in. Maybe that's the key. Maybe what I need is a lens that creates an at with default. That's the trick. Rather than trying to make a monoid out of this, because that would work, it would be ugly. Is there in a lens at? Is there something like this? Or is there that somewhere else, actually? Look at traversal. Probably not. Because it's not exactly a traversal that I want. And at, there wasn't anything, I think, but I could I could look at combinators and see if there's anything there. Hmm. No, I don't see anything like this. Wait, no, this isn't there something called or in. If I look at or and I add lens. Ah, there isn't. What's the syntax to add something? It is package lens. Or of. No, that's not what I want. I thought there was a way. I thought there was a way to do an at and then. My knowledge of lenses is partial. If you want to be able to insert missing values, you want at. I'm surprised. No, I know there is a lens for this. I just don't remember which one it is. Set with index? No. Very zen, indeed. Phew, 19. Okay, that's a lot. I know there is something. I know I've used it in the past. I just, for the life of me, cannot remember what it's called. Because at, I think, with a monoid instance would do the right thing. Here we have the or of that I was looking for, but that's the wrong one. There's so many things in this library. Preview? No. I'm losing some time by looking for this. I know there is one, which is why it bothers me that I'm not finding it. Okay, well, let's. If this were a thing in there, would it be called default? Would it have something? No, it doesn't have anything like this. Would it be something on the base of at? No, I don't remember. I do not remember. Okay, I'm gonna give up on this. And instead try to see if I can find the answer on Stack Overflow or something. I know it's possible. I know I've done it. I just don't remember how it works. Okay. Lens at with default. None. Okay, there we go. I could have saved a lot of time. So this is what I was looking for. I want to do... I'm gonna make... Get block will be a lens... It'll be a traversal from the lowering state into a given block, and get block for a given label, and that will be the combination of ns blocks at label non default block, basically, where the default block is a block that contains, and here is where I need to remind myself what there is in the block. There's that. And by default, panic here at the end. This will be overridden. It's fine. So that's the default block. Okay, so that should be fine. That should give me the traversal I require. And here, as a result, rather than this being blocks modified by, this is going to be get block label dot block instructions modified by appending an instruction. Block arguments modified by adding the register. Set terminator will be the same thing, but block terminator, which will be set at the terminator. Okay. Hopefully this will work. And this is a traversal prime. In scope label, because it's the argument that I have failed to name. So that is not correct. So it must be... either this, but there's probably some way. There's nothing called... I searched for it earlier. To the head of a non-empty container, so that's not what I want. Maybe actually just _1 is what I want. _0 actually probably, which is the same thing. Yeah, okay, just index 0 is probably what I want. Or first? Is there something as first? Yeah, it's fine. At index 0, and that should hopefully give me a maybe. So it executed something that takes maybe, okay. Lenses, why are you so complicated at times? Oh, I guess indexed might be what I want. No, it's not what I want. No. So at is what I want, I think. But at is for keys, therefore I want the index version. Okay. And is list something that can be indexed like this? It is, okay. So this is not a problem of the lists are not compatible with this. It is a problem of this does not. It's not compatible with what use expects. Why? Because this ends up with a traversal. This, so I give my index thing 0, which is the type of index of the list, and I end up with a traversal from the list to the kind of value of the list, which in the case of this, of a list, will be... was useless. I don't have the... I have the source. Okay, that's what I wanted. Oh, the type is A. Interesting. Oh, but it's because it's a traversal, of course. Yes, because it is traversal. Okay, and if I go back to the getters, where are you? Here, and I go back to use. It expects a getting. What is the difference between a getting and a traversal? You can pass the function a lens getter traversal. Okay. So why is that traversal that I'm giving it not accepted as a valid way of using it? That's annoying. Okay, I'm just not gonna bother. I'm gonna say, okay, apply this lens, and the function we're gonna apply here is safe head from the module safe. I am not gonna continue messing up with lenses. I am losing enough time with this. This is fine, it should work, except I don't have safe as dependency? Fascinating. I don't have safe. Huh. Is there something in the prelude now that I can use instead of that? That given a list gives me of A gives me a maybe A? List to maybe, I suppose. Safe head is what I want, kinda. Or head may in safe is what I want. I thought I was depending on safe already. Fascinating that I'm not. Okay. That will go therefore into... Oh, do I need to... I'm not going to import a whole thing just for that. I'm going to write it myself. This is use the thing, and then I apply a function that does a case of this, that just does a from maybe. And in the case, uh, just list to maybe, I think. Let's try if I do import data maybe, import data list, list to maybe of an empty list nothing of, that's what it does. Okay, so list to maybe is what I want. And that, where is list to maybe defined? In data maybe, perfect. There we go. That should be fine. Oh, interesting. Why does none? Okay, so let's look at the definition of none in lenses. Oh, that's not exactly what I wanted. It looks like. It's not exactly what I want. It looks like from this example here. Oh wait, no, no, this one. So I have a map of hello to 1 at hello non-zero. Huh. So maybe none works, but it's not the one I want, actually. Which means I will want something that is an ISO between maybe A and A, I think. Except I can't spell that. Where was it? Was it in? It was in combination. I've lost it. Okay. Lenses, lenses. Yeah, let's go to the wrong one and just content and combinators. Well, actually, let's do it like this. I want to find none is an ISO prime. Okay. Why can't you find that? That is literally the type. Okay. Is given an A. That's the only one. Okay. I guess I could do that and use the a basic predicate, I suppose. This is frustrating. Hello. I'm fine with the Haskell part. It's just the lens that here that is a bit annoying. I am trying to use lenses for accessing the shared state that I'm using as part of one of the phases of the compiler. And I want a lens that gives me a value in a container if that value, like, and provides a default, which I have found, but it requires an equality constraint on the value because it removes the thing from the container if it doesn't exist, which is not exactly what I want. But I can add, trivially, I think, the equality constraint. That's not going to be a problem. What bothers me is it should not be required. And I am trying to figure out lenses can be tricky, and some of those lenses are really annoying. So maybe instead of putting an equality constraint, I'll use the anon one instead. I haven't played with a lot of other functional languages, to be honest. Haskell was my main. Well, I've done some OCaml a long time ago, but the Haskell has been my main one for at this point over a decade. Wait, there's a solution that actually doesn't require doing any. Can I make a custom lens? Let's have a look at actually how this is implemented. Because basically what I want is I want this version. Yeah, this is just basically ISO from ABA. With a default that is always just B, I suppose. What is ISO defined as? Yeah, Haskell is, since I've discovered it, it has become my main language just because it is that fascinating. Wait, why is okay? Okay, yeah, no, this is stuff I do not understand. I am just gonna use. I will dig into this off stream because I don't want to derail the stream more than it has already been derailed, which means here I'm going to use the anon default block and I'm going to use a predicate, and that predicate is going to be const false, basically. And that should work as expected, I think. Except here and here I can remove the equality constraint and I'm finally free of this part, I think. I am not. I am not. let's see the example that is used for none. This, I think, is something that happens regularly, is not the right, but it happens often enough of I'm trying to use lenses because it will make things a bit more elegant, and I end up losing a bunch of time on something that is not that important. Interesting, because that looks like... but I suppose an ISO thing is not something I can use in the context of the state monad operators I'm using. So that means... Okay. That means this becomes a traversal from a hash map of label to block and gives me a block, and that is at the label and if and then non const false default block, which I can rewrite even... No, that's fine. And here this becomes then I get the lens to the blocks, which is the hash map, and I modify it. And the way I modify it is I do get block label, which gives me a traversal to the block, and the instruction within that gets modified by doing this operation. Here I modify the state by accessing the block thing, and on that hash map I do a get block label, and I then get the block arguments that I modify by doing the append at the end. Yeah, take your time. And here, likewise, I modify the state by applying a function on that lens, which is get block of the label, and there we go. And that should be this. That version should be fine. Almost. Did I use anon wrong? Yes, it is the default block first and the const false afterwards. Okay, so that works. Can I actually do then ls blocks this and have the traversal be from the lowering state? That work? Yes, so the problem was... Okay, so here I can reverse that. That's good. So I can do that instead, I think. The problem was just with the order of the arguments to anon. Yes, that was the problem. Okay. As usual, we lost a lot of time on lenses, but now this part of the thing works. Wait, am I not using list to maybe anymore? Oh, but maybe it's already imported from the prelude. It is indeed. Which is why, indeed, this import is not required. Make lenses... Oh, of course, I am not exporting... Wait, I'm not using them at all. I guess I'm not using them at all. So I don't need actually to make lenses for this. Which means I don't need to prefix them with underscore. Yep, and here as well. And here as well. Tail is partial, do not use tail. That's fair. This is going to be a drop 1. Oh, do I have actually my prelude again? What do I import from list? I don't import drop, interestingly. Okay, so import data list drop. I guess rather let's do it qualified as L. And break shadows something which is defined in list. Oh yeah, I suppose. I could even actually do the thing where I give them the exact same BS continue, BS break, and I could do that. Ah, but those are the wrong. Okay, so I can do that. Why are you unhappy? What's wrong here? Yeah, I can see that you're unhappy with this. It's just a matter of indent. Yes, it is break. It was indeed just a matter of indentation. Okay. Okay, and now we're back here of uses non-scope. I don't have, oh, I simply don't have lens in scope. When just M, that is from import control monad extra. Set parent. I think I've called it register parent. And there we go. Now I have errors I expect. Process expression is a function that is currently missing, that given the label of the current block, given a resolved expression, which is a typed expression, will modify the current block to insert all of the required operations in the AR, and this will be an operation in the lowering monad that will give me a register, which will be the register in which the result of the expression is captured. Process expression, given a current label and a typed expression, is for now unimplemented. Okay. Here. Aha. So here, a jump, an unconditional jump. I am indicated here that we are at the end of a block of instructions. There are no more instructions to process. And I am in a case where there is a fall through in the current state. So I'm saying, okay, this block then terminates by always jumping to the next label. However, we don't jump to a label, we jump with a target. As in, what value, like where do we jump and what values, what register do we give for each of the arguments. However, since all of the parents must be processed ahead of time, like a block cannot be sealed, therefore its arguments cannot be known until we know all of its parents. At this point, there is no arguments to give because at this point the arguments have not been determined. Therefore, this can be a target. I'm gonna make a function for this. Target, where are you? Make target given some label makes a target, and make target is given some label is a target of that label and no arguments. And that becomes make target next label. There we go. Make target. Okay. Oh, it's because I have the wrong number of arguments. I have the wrong number of arguments for my report ice function. Likewise here. Statements unused. Yes, that's correct, because since I don't have yet the error reporting mechanism in this part of the code, this statements thing is only used in things that are commented out. So for now, underscore, so that the compiler knows I am not planning on using it. Define method used. Yep. Okay, so that compiles. So progress. Now, expressions will be the interesting and difficult part. For now, let's continue making progress on the statements. What statements have we not handled yet? We've handled continue, break, return. An expression statement will be the easiest because unless I'm mistaken, it should just be this should just be a call to process expression, basically. Like we get the register that we need by, oh, I need to do something else. I need to do something else. So this will be a process expression here that given the current label and the expression we found, okay, add a bunch of instructions, do all the registering of arguments, do all the stuff, and that gives me a register. Do I need to use this register? I guess it depends. No, I think in this case I don't. I don't need to use it because it will be stored in the state as part of the value, whatever, if this was a function call or something, will be, yeah, it will be put in the state as being one of the registers there. And here I have nothing from this expression that requires it. Therefore, here I can just void the process expression. Perfect. And I don't think there's anything else I need to do after this, which means I can simply step in block. We are still on the same block, and now I'm going to need the statements. And I just continue, step in to the rest of the statements. Okay, that was an easy one. Well, it assumes the existence of this function that doesn't exist yet, but, you know, beyond that, it was an easy one. And now we are left with let, while, for, and if. So let is going to be a special case of an assign, I suppose. So a let statement will have the let info as an argument. I guess it will serve as practice for how you're going to handle assignment expressions within expressions when we do process expression later on. So a let statement, we have a let info that, as we know, contains the name, the type, the expression. So what we're going to need to do is we're going to register as part of the registers in this block a new value for whatever. Well, first, I suppose we have to get. I guess we have to process the expression. Which tells us, okay, this expression is processed in. Like the result of this expression is this register. And what I need to do then is add that to. Not there. I need to. I know. So I've expanded the expression. I've like transformed it into a series of instructions. And I now know in which register the thing is stored, but I know that now this particular local variable in this current block maps to this register so that future use can look it up. So I think the only thing I need to do after this will be to look within my current state. I'm going to have the same problem of lenses. That is annoying. So maybe I'm just not gonna, yeah, okay. I'm just gonna, not gonna bother. The registers, I'm gonna modify the hash map by doing an insert of, for the key, which is the current label, and a role, which is gonna be, the role is gonna be local variable, let variable, there we go. Or do I just want the identifier, actually? Do I just want the identifier? Let me think about this for a second. Because I think a register will have to be pointing to a function argument or a let variable, nothing else. Do I just need the identifier and nothing else for the scope? I guess it will depend on what I do when I encounter other things. Constants will have been inlined. Type and built-in function will not appear in those cases. Type parameter makes no sense. Placeholder makes no sense. Yeah, I know for a fact it's going to be one of those. In which cases do I get a function pointer again? This only shows up, okay, in context. Yeah, it doesn't show up, it never shows up in a value context. It only ever shows up in the type context. So I think, yes, I will never need to do a lookup over a register for something that is not a local variable or a function argument, meaning I can probably, it's enough to only use the identifier as the key here, which means here, hi, yes, everything I do on stream is on YouTube. I am up to, I think, last week's streams. This week's streams are not on YouTube yet. I have a secondary channel which I don't remember if actually do I have a link there on the GitHub page of the project? Where does this thing go? Oh no, it goes to the playlist that has. That's a very good shout. Then, oh no, here we go. All streams are archived on a dedicated YouTube channel. There we go. And the latest is from a week ago. So yeah, I'm missing only a few streams. Some of the very first I'm missing, but since I had a lot of hardware issues and the stream was completely broken, not a big loss. I'm only missing a few streams because I failed to download them in time because the Twitch retention is very short. But 99% of them are on here for the last, like, started in March, and there's been a few. I'm not always the best at uploading them, so I'll try to finish uploading the ones from this week before the weekend. Okay, so since we have made this change, I no longer need to create a fake local variable or anything. I can just say the name x, whatever it is, points to the value. And so the name is coming from the let info. That is part of my AST. So that's just the let name. And the register that this name is pointing to in this block after this will be this register. Okay. Perfect. Now we only have a few more statements to deal with. Because we've done expression, break, continue, return, let. We have if, for, and while. Which are the remaining cases that we need to handle. So the interesting bit here is this is where we're going to have our recursion into inner scopes within our the scope in which we currently are. So let's do if first. I'm just gonna prepare this so that it's at least syntactically correct, even though I'm not gonna do it right now. So, unimplemented. There we go. Okay, so what do we do in the case of an if? So an if will be, if I look at the research paper that, again, I'm using as the basis for this thing, it will be something like this. I will add the condition. So the expression of the if will be translated into something that gives me a register, basically. And then the current block will end with a branch instruction, which if the register is 0, goes somewhere, if the register is 1, goes somewhere else. And I'll arbitrarily decide which ones means the if, which ones means the else, and I suppose I'll just use that as a boolean, therefore 1 for the thing, for the if. So the case of the if will go to the then. If there is an else, then the 0 case goes to a new block. If there isn't a else, it goes to a fall through, which is where do we go after the if, basically. So this is where a bunch of the things we've been doing earlier with the functions in the monad will come in handy. Because first, we must create a label. Oh, okay, I'm gonna stack something quickly. I will make a note for later that here all blocks is the result of use ls blocks to do filter out unreachable blocks. And the result will be pure function start label all blocks for now. I'll explain why in a second. So when I step in a block and I convert some kind of instruction into dir, I check that the current block is reachable. The point of this is if actually the point of this is basically if I end up if I do an if then an if else thing, and then there's code afterwards. If both the if case and the else case contain a return, then neither of them will reach this block there. Therefore, this block doesn't need to be processed and doesn't need to exist, basically. So I will definitely want to filter out unreachable blocks, because some blocks might end up existing despite, like, it might be in the list of blocks despite the fact that I have actually never been through them. So, however, there is a thing I want to detect, which is I want to detect if the block I'm trying to process is not reachable and it contains instructions, it contains stuff, that is an issue, right? Like that means there is an unreachable block. Yep. Okay. So I need to handle this case. So let's do that. So is reachable of the current block. If reachable, I don't like to do it that way. That's a bit ugly. Let's have a quick look at control monad extra. Icon type. Does it have an if m or something like this? Yes, okay. Yeah, I'm gonna do it like this. If m is reachable current, then go, which is gonna be my inner function that does the thing. And otherwise, I'm gonna do the else block here as a do block. Or rather, I'm trying to do like this when not null instructions unimplemented for now, which will at some point, instead of being that, emit warning, unreachable code. There we go. So if it's reachable, go to the go function. Otherwise, we are in an unreachable block. The only thing we do is, I guess I could do unless null to avoid a negation, unless the instructions are null, in which case we can just ignore the thing, emit a warning, which for now is not implemented, and we'll just crash. Okay. And now I have to replace this with, and go is case instructions of, and I'm gonna have to indent all of this, which is fine. Okay. Now, back to what we're doing with the if. So here I'm gonna need to create the pass-through label, which is where we're going to go next. So that's gonna be a make label. I'm gonna need to create the if block label as well, which is where we're going if the condition is met. And we are gonna need an else block label if there is an else thing. And the else block label is going to be let's have a look at the, I'm trying to do the usual thing. I'm going to put the AST here on top just to have the stuff here. There we go. If there is an else case, I guess I can just do it with like, not even that, I can do it with a maybe. I apply a maybe function on this thing. If there is no else case, then the case of we don't go into the block is just the pass-through label. That's where we go. But if there is, then what I do is const make label, which is a monadic will be a monadic operation, so this needs to be pure. Okay, so if there is an else block, I create a label for it. Otherwise, I just reuse the pass-through label. Perfect. Since those cannot have any other parent than the current one, then I can seal them, which is convenient. So I can finish the current block. So the current block will end here. So I will terminate the block with a branch instruction. And the first case will be the if block label. And the second case will be the else block label. So this is where the current block ends. If we go back to this schema here, it ends here and it goes either to the then or to the else. And if there is no else, this label is the same as this one. So it goes to here basically. So that block has ended. I can register the parent. I know that from here I can go either to the if block label. So current is a parent of the if block label and of the else block label. And then I need to go process those blocks and then resume what I was doing with my instructions. So at the end, I'm going to have some recursion here. So I have the with inner scope thing we're going to use. And at the end of that, oops, set terminator should still be there. And after doing something with the inner scope, which is the if of the stuff, at the end of this, I'll have done all of the if block, else block, the everything. I will be able to then step in block with the pass-through label. So I continue to that block afterwards with the rest of the statements that we need to process. Okay. Now, what do I do with the inner scope? This will be processing the if block. So what does with inner scope require again? It only requires the fall through label. Where do we go when we are done with this inner block? So that's the pass through label. Oh yeah, fall through, pass through. Fall through definition. Pass through. I'm not sure which one is the correct one. It's not a continuation because I'm using continue in the sense of a loop already. Resume. Resume is a better term. So I'm gonna modify a few things. Let's go back to here. Current resume label, actually. Current continue label. Current break label. This is going to be a lot more explicit. Perfect. Which means I need to change. This is now current resume label, continue label, break label. This is the resume label. Resume label. Okay, that's the end of that. So we can go back here. Here with the inner scope, which will do the thing of like change. If we are in a loop, still keep the current state of like where do we go at the end of this, but we'll keep this resume label as where we resume at the end of the instructions. With that inner scope, we need to go process I guess this function will not just perform a step, it will recursively process the entire block. So maybe I should call it process block. Okay. So within the scope, the inner scope of the if block, what we do is we seal the if block label because all of its parents are already registered. It's fine. And we can then process block of the if block label and the if body. And that will be all of it. That gives us that is done. We've done processing everything. And we can then resume by processing the resume label with the statements that were left in our current block before we forked for the if. However, if there is an else, I might need to introduce a new function for this. Okay. So if there is no else block, there is nothing to do. If there is, I guess I can do it like this. For if else, that's a bit inelegant, but that's fine. And the function I do is a case. And if it's an else block with a bunch of else body, basically, then we do roughly the same thing with the inner scope of the resume label. With the inner scope of the resume label. Actually, I think this I can do that within this with the inner scope. It will always be the same. There's no loop. So that's all fine. I don't need to do the with inner scope here. I can just do that. If there is a else body, I can seal the else block label. I can seal the else block label and process. Hello, it's going okay. I got stuck a bit earlier on some lens stuff, but now that is done, I'm back to having fun with the translation of the creation of the control flow graph in the lowering into IR. This is an unplanned stream. I usually stream on Tuesday and Thursdays, but I got stuck yesterday evening and I wanted to make progress, so I'm back on it with not my usual setup, no camera, nothing. A bit of an ad hoc stream. So here we encounter an if statement. We create a bunch of new block labels and we indicate that the current block ends in a jump. This is basically doing this. The if here ends with a jump to either of those two blocks that are like have each a distinct label. There's also a resume block at the end here for if there is no else block, nowhere to jump, and also for the then and the else to know where they're supposed to go, basically. So I'm doing all of this with the inner scope that like contains the resume label. We seal the if block label and we process that block. If there is an else block, then we seal it and we process it. However, and this is where I'm going to need to introduce, I think, another function, because we could have an else if. And if we have an else if, we're back to having an if info. Oh, but that's not exactly the same thing. Because here we need... The else if is not exactly the same thing. Because I cannot create a resume label here. I already know the resume label. It is always going to be the one that we have created here. We always go there at the end anyway. So I guess, okay, I still need to introduce something else. So I'm just gonna, for now, just unimplemented. I'm gonna hide this for a second. And let's introduce a new function. A local function to here, so align with this. Do I want to put it before or after? I think after is fine. So this is going to be a process if, and it will take a resume label as an argument, which is where do we go at the end of this if, and it will take the if info. Okay. And what we're going to do in this case, and I'm just going to move a lot of that stuff. This is going to go in it. So first, do we need to create a label for an else block? And that is only the case if there is an else to this if. If there is, we call make label to create a new label. Otherwise, we reuse the resume label, because in the case where the if doesn't match, we go to where the execution would resume after the if. It's the same thing, it's the resume label. Now, we terminate the current block. That part of the if is always correct. And that current block will terminate with a branch, which is in the case where the register... Oh, branch requires a register, I think. Branch requires a register. Where are my terminators? Yes, branch requires a register. So I need to do something else. I have forgotten something here. So this is gonna be process if resume label and the if info. What I forgot here, so I have the if block label and the else block label. Here, the branch will require to knowing what is the register that contains the Boolean information on that decides whether we go to the if part or the else part. And that register will be obtained by first, before we terminate the current block, we need to add the instructions of the condition. Not what I was looking for. I am looking for the AST. It's the if expression. There we go. So first, we need to process the expression, the if expression, so that in the current block of the IR, we are adding all of the instructions and statements that compute the actual value, the Boolean value of whether we jump or not. That tells us which register the value will be in, and our branch will be branching based on this register. There we go. So we create an if target. We create an else target if there is an else. Otherwise, we reuse the resume label, where we go to when we're done with this. Oh, I suppose that means, yes, if else are the case where we can have a block with more than two parents, I suppose. There's a bunch of if, else, if, else, if, else, if, and so on. They will all have the same block as resume target. So that one will have more than two parents. That's fine. The assumption that they had only two parents wasn't something I have built any code on. So that's good. So we branch. We finish the current block with this branch after processing all the expressions in there. We register the current block as the parent of both of those. Aha. No, that's correct. That's correct. I was going to say, is that redundant in the case where this points to the resume label? It is not. Because the if block and the else block in the case where they contain something will then have to point to the resume one. So it's fine. That's correct. And that is just a consequence of this being a branch. And then with the inner scope that will contain for the duration of this stuff, the fact that we are supposed to resume there in the case where we run out of instructions to process, we seal the if block label and we process it using the statements in the if body. If there is an else, in the case where it's just an else block, we seal the else block label, we process the block. In the case where we have an else if, we have another if info, and we can just process if, I put it on the line, with the same resume label. Where is it? That's something that's annoying. Something that's annoying is that I'm gonna be nesting a bunch of with inner scope that do not do anything. Can I avoid this? I think I can, since this is all gonna be just to say what do we do in this context if we run out of instructions. I can do it once here. So with inner scope resume label. Process if. And now I don't need to do it here, which means that even if we have a bunch of recursions because we have a bunch of else if, they will all be operated within the same inner scope, which is fine. Okay. And that should be everything. Nope, missing one thing. Before I process the block here, at this point, either the if case or the else case will have reached either the end of the instruction or a return instruction or anything like this. Therefore, after this, we will be done with processing them. We will know where they jump. We will have the full list of parents for the resume block. Therefore, we can seal it. So seal the resume block on the resume label. Seal the resume label, process block the resume label with the rest of the statements. There we go. That wasn't too bad. That wasn't too monstrous. Now let's do while, because I think while is going to be easier than for, especially since for at the moment, I might just not implement for at all at the moment, because I don't have range instructions at all, nor do I have containers yet as part of the analysis. Therefore, let's not bother with implementing for. Let's just leave it unimplemented for now. But while, I am able to implement. So, what do I need for a while? I need a block for the condition. The block for the condition will be a new block that's like different from the previous one. So we will need to terminate the current block to always unconditionally jump to the condition of the while, where we perform the computation for the condition. Then there we have a if-else jump. Basically, we have a branch. One of them goes to the body, and the body will be something that resumes at the condition. And yeah, okay, so let's do that. So this is going to be somewhat similar to what we do for a if. So first, we are going to want to create a new block for the while condition. So that's going to be the condition label. Just a label. Then we are going to have I was going to say, can I do an optimization where if there is no instruction in the loop, then the label for the loop is just the condition label, basically? Where like in the case, if true, we just jump back to the condition. This is an optimization we can do later anyway, where if a block is just has no instruction, no argument, and just an unconditional jump, then we can perform an optimization later on where any jump to that block becomes a jump to the other one. So that can be done later. Let's not do it as part of this phase. This phase is already complicated enough. So this is going to be the block where we go for the condition. We are going to want to have a loop block label, which is going to be where the block for where the loop is going to start. And we are going to want a resume label as well, which is where do we go when we are done with this. Okay. At the end of this, we're going to do a bunch of things in the middle. At the end of this, we will have processed the entire loop. Therefore, we will know the entire set of parents of the resume label. So we will be able to seal the resume label. And we will be able to process block the resume label of the rest of the statements that we had after this while. Okay? Now, I guess the current block will end. The current block will end because the condition needs to be in the condition block. So the current block will end with an unconditional jump to that block. So, as usual, set terminator of the current block. It ends, and it ends with an unconditional jump that targets the condition label. And as a result, I need to register as a parent the condition label has one parent, which is current. This is where it's tricky, because in every case so far, I have sealed the thing before processing it. Here is where I cannot. because I don't know yet if the while loop actually has a parent that goes back. This is where I'm gonna need to process this. I need to seal this last. So I need to process it first, but seal it last. That's fun. Okay. But okay, I've indicated that the current block has ended by setting the terminator. I've indicated that it is an unconditional jump to the condition label, and that as a result, the parent of the condition label is my current one. Now, in the condition label, I can fill the condition label basically. And filling the condition label, there is no process to do. The condition label is purely I need to know the register, which is the process expression of the while expression, I suppose. Oh, process expression requires the label. Yes. Process expression current. Here, this is not the label. The current label at this point is no longer what was called current. It is now condition label. This is where we're putting those statements. This is current. Oh. No, it's not. It is not, because if I am in this case, if I'm in the case of an else if, where I'm putting the instructions, from where am I jumping, where am I setting the terminator, is not current, which is an argument of this function. It is the current of this function, which means I should make it a dedicated function to avoid that confusion. Which will take as an argument, it's going to be very similar to this. Except it's going to take a if info resolved. There we go. And it's going to take two labels, I suppose, the current and the resume label. So now that's correct. And here the recursive process if in the case of an else block, because yes, indeed, the process expression goes into the current. Now that's correct. And from the current, we jump to the if or to the else. And that means that in the case here, what becomes the current in which we do those things is the else block label. Perfect. Okay. So now, so if process if here is current and resume label. For the while loop, we are going to, so we indicate that current ends and that it jumps to condition label. Now we process expression in where the current is condition label and the expression to process is the while expression. That gives us the register where the result of the expression will be stored. And we can then close that block, because the terminator of the condition will be a branch where the positive case is the loop block label and the negative case is the resume label. If true, we go to the loop block. If false, we resume after being done with the execution. And the register on which we do the branch is, of course, this one. I'm going to put this on a new line. There we go. And I might do that for the if as well, just because those lines are being a bit unwieldy. Okay. So I'm going to actually do that. We need 3 blocks after the one that we're currently finishing, because we encounter a while the current block has to finish, which is the new block for the condition. And by block, I mean like a node in this edge of our control flow graph, basically. One for the loop block, and one for afterwards, for after the loop, basically. The current one ends and jumps unconditionally to the condition, which we can register as like, okay, jump to the thing. I am almost tempted to make register parent a part of set terminator. As in, I am setting the terminator, and as a result, I can introspect whatever I've given as the thing to always set the parent. Because I will always do both. That's always the point. Yeah, I'm going to do that right now. I'm going to stack something on top of something else. Let's go. Which means I'll be able to remove... Yeah, that's going to be better. Perfect. I can remove register parent from this. Perfect. So now when I do a set terminator, I can then do a case of the terminator. And if it's jump or branch, here we do nothing. Here we do nothing. But if it is a jump to a target, we can do something. And likewise here, we can do something. I think this one already exists. Let's do that. We can... What is a target again? A target is something that contains a label. Okay. So I can register parent of the label of that target as being the label, the current one we've just finished. If we branch to 2 different ones, then I can register parent of both of those. There we go. So now that means I don't need to like align this, it's not required. I can go back to this and register parent. Here, set terminator as the jump will always do the register parent. I don't have to do anything. Set terminator as jump to the next label will register the parent. I don't need to do it explicitly. Set terminator as a jump register parent, not required. Perfect. So that removes a lot of redundant code. So here we are saying I am ending the current label by always jumping to the condition. The condition will only contain the instructions for processing the expression of the condition. So that's going to be all the instructions that are in it. There's not going to be a if or a while because it's purely an expression, but those go into the instructions of the condition label. And it terminates immediately afterwards by using a branch on this register that we got there. And in the positive case, we go to the loop block. In the negative case, we go to the resume label. Now we need to process the loop block. Which we can do as we can seal the loop block, and we can then process block of the loop block label using the while body. Which, oh, that's not entirely true. I need to fix this. This is not correct. At the end of this, I will have processed everything. I can seal the condition label, which wasn't sealed because we didn't have the last edge from the last block of the loop block back into it. But now we have it because we have processed the block. I can seal the condition label. I can seal the resume label, and I can resume dealing with statements that appear after the while block. Okay? So now the last thing that's missing is this is not going to be, this process block needs to be aware of where do we go when there are no longer any instructions, where do we resume, where do we break if I encounter a continue or break statement. And I have a function for this, which is with loop, which takes resume, continue, and break. I think resume and continue are the same thing. So maybe I don't need to do that. For a loop, I can always just say that it's the same thing. It's the continue label. Because if we do continue within a loop, it goes back to the condition. If we run out of instructions within the block of a loop, it goes back to the condition. So I think, yeah, I don't need all three. Condition, continue, and break are enough. So with loop, continue is the loop, the condition label. The break will be the resume label. And what do we do within this scope? We process the block of the while. And that starts as being the loop block label. Okay. That is handling a while block. Handling a for block will be very similar. The only problem is for works on like containers and ranges, and none of that is handled yet as part of the analysis. Therefore, there's no point in trying to do it. We can't even test it at the moment. Which means when this compiles, we're done with the top level processing block and handling of statements. The only thing we have left, with massive air quotes around we just have to do process expression next. So let's try to compile this first. Then scope identifier, that's easy to fix. Fall through, I haven't changed that name. Okay. This is current resume label. Current continue is now called current continue label, and I have the same error here. This is currently current break label. here there's nothing called because it is the if expression coming from this. Sorry, not if expression. What did I just say? The let expression coming from this let info. Yes, of course. I did remove all the register parents from this part of the code. I didn't do it from this part of the code. So here I do set a terminator as a branch. I don't need to register the parent. That's done for me by set terminator. Okay, perfect. And here I am missing. Yes, I am not giving the if info as an argument. Unused record wildcards. Yes, of course. This for info stuff is not used because the for thing is unimplemented. Okay, so this compiles. Without the expression, it's going to be hard to test. So I think for now, I'm just going to power on and just continue, like soldier on and just like continue doing some stuff on the expression. Because for now, it's going to be very, very hard to test. So let's do that. This is basically going to be a gigantic case where we're going to need to deal with all of the different possibilities. Let's do the usual thing. Let's open the AST on top of the screen and let's have a look at what an expression can be. Oh, I don't have. Interestingly, I don't have yet a warning for an expression that does nothing. I should have that. For instance, if a function does, like, one of the statements is 3 plus 4, that's a expression that doesn't do an assign, that doesn't do a function call, that doesn't do anything. It's pointless, basically. I already have ways to test if something is pure in that sense, as in perform anything could happen. I could test that the top level expression thing is not pure, and if it is, emit a warning. I'm gonna, as usual, stack something else on top of the thing I'm already doing, and I'm gonna go back to core in the analysis phase, and I'm going to expression statement there. Oh, no, I already have it. I guess I'm not using the purity information for that. I could perhaps... Can this be simplified using gathered purity information? Because there's also a thing of like, if this is pure, can I just remove this code entirely? It will never be executed. It's pointless. Or do I not do that as part of this phase because the analysis phase is not supposed to change anything that is like as important as removing code? And do I leave that to the optimizer? And I'm tempted to leave that to the optimizer because the optimizer will do that if we have such an expression like this, like that does like a 3 plus 4 at the top level semicolon and doesn't do anything else. This will be translated by the lowering into IR into a add instruction that will add a result to a new register, and that register will never be used. So the optimizer will be like, oh, this register is never used. That value can just be entirely removed. and we'll be able to remove a bunch of things. So I think I'm going to leave it as part of the optimizer in the same way that the simplification phase does not remove things, like does not remove things where I know for certain that a value will be known at runtime. This is something I might want, but later on. This is something I will do later on, I think. There are things such as, if I know at compile time the value of a if, I can simplify the control flow graph. I don't have to handle the else if I know for a fact that it will always be true at compile time, like an if true, for instance, or if false. I can optimize those. But maybe, again, I will do as part of the optimization phase. This might be a better way to do it. Okay, so let's avoid stacking more things on top of what we're currently doing, and let's come back here. So here I want to process an expression and translate that into a bunch of instructions. Can I try? Let's do that. Even at this resolution, it's fine. So what kind of expression do we handle first? Path expressions are going to be complicated. Let's start with the simple ones. So how do we deal with a Boolean literal expressions that happens to have a Boolean b? Well, that is going to be easy. We create a register. Where the result is going to go. And we add an instruction. How did I call that one again? Append instruction. There we go. I append an instruction to my current block, which is assign Boolean, and the register is the one I have just created, and the value is this Boolean b. Now, registers, do they contain type information or not? They do, okay. So I suppose that my make register expects a type. It does. And my type is one of those. Okay, and here the type is already known. I don't have to translate the type. So this is make register of a Boolean type. Okay. So that's an easy one when we encounter a Boolean literal expression. That is, we create a register, and we said that the instruction is assign that Boolean value to the register, which the code generator will translate into something, and we return just the register, so that any parent thing knows how to handle this. Now, okay, let's continue with the easy one. I'm just going to copy that and paste it for int literal expression and character literal expression. Whether this is going to be an int type, and this is going to be a character type, and otherwise it's going to be exactly the same thing. We create a register. We append an instruction to our current block, which is just assign that value to that register. And that's it. I am not going to handle string literal expressions because I don't have any support yet for any dynamically sized type, and strings and arrays will be, because I don't have a heap, I only have a stack, and those are going to be a nightmare. So for now, those are unimplemented. A reference expression, do I need to translate a... what will happen to a reference expression? I think reference expressions will be no ops. In my IR. Unless I want my IR. No, okay. As far as exporting to Piètre is concerned, reference expressions could be purely, they appear in the language only for one very specific purpose that doesn't need to be captured in the AR. So it could be fine to just have them be no ops. However, I will probably want, if I want to do this thing where I export our IR to the LLVM IR, then I won't be able to do that, I think. And I will need to capture the notion of references in our IR for that. But that is going to be a problem for future me. And I don't care about them for now. So for now, reference expressions unimplemented. No need to do that for this evening. Okay. So let's start some of the basic mathematic stuff. An int negation expression that contains a sub-expression. An int negation expression that contains a sub-expression. We are gonna need to first process the expression in the current block, which will give us the register in which the result of the computation is stored, whether it's just an assign or anything like this. And then, well, not an assign, it would have been optimized away at this point, but, you know, an addition, something like this. And then we will emit an instruction, and this, I will need to create a new register for the, I will need to create a new register for this. So that's previous register here. And the result will be this new register I'm creating. I don't need to do type checking. Type checking has already been performed, which is going to be an int type, since it's an int negation. And the instruction in that I'm going to append to my list of instructions is going to be, in my current block, a negate integer instruction that targets this register, and the source of the thing we're negating is the previous register. A Boolean negation expression is going to be very similar. We get the previous Boolean expression by processing its expression in the current block. We get the result, the previous register. We create a new register of type Boolean. We append the instruction in our current block, which is negate a Boolean, targeting this register from the previous one. Okay, then addition expression takes two sub-expressions E1, E2. The first register will be the result of processing the first expression E1. The second register will be the result of processing the sub-expression E2. And we perform E1 first, because if it panics, we want to panic like it's left to right, so we always process E1 first, and then we create a register for the result to do handle string concatenation. Because for now, because the addition a plus can be either string concatenation or int addition, but for now we don't have strings, so for now it's always going to be make register int type. And I guess I'm going to actually target. Target's going to be this. Oh, and I forgot to... Okay. Here, those part of the block do not return the register in which the result has been set. There we go. That's a mistake. So here, for the addition, we create a register of type int. We append an instruction to the current block, which is an add instruction. The targets R1 and R2. A subtraction expression. It's going to be basically the same thing, except string concatenation is another thing that needs to happen. And this is a subtract. Well, not bytecode, but, you know, IR statement that we output in our function, targeting this new register we have created. And I need to not forget to return the target. The compiler will warn me about it, but, you know, still. I guess multiply, divide, modulo, exponent are going to be the same. So for multiplication, division, modulo, exponentiation, I can just copy and paste this. This is multiplication. And the corresponding operation is multiply. This is modulo. This is division expression. This is a divide instruction. This is a modulo expression, which becomes a modulo instruction. And an exponentiation expression becomes a exponent instruction. I'm tempted to just... Yeah, this is very repetitive. So I am tempted to introduce... where binary int operation with the instruction is going to, and the E1, E2 is going to be that. And as a result, this is just binary int operation exponent E1, E2, and this becomes replaced by the instruction. There we go. And I can change all the previous ones into that. This is modulo. This is division. This is divide. This is multiply. This is subtract. Here, in the case where it is not string concatenation, then it becomes a binary int operation. Add E1, E2. There we go. That's a bit cleaner. Okay. That should be all of it for the basic... I guess I could do the same thing for the literals, actually. But it requires... Oh, actually, this is assign I and assign C. Doesn't make a big difference. Okay. So that's the literals and the basic reference ignored and the basic mathematical things done. Then I suppose it's all of the comparison expressions. And the comparison expressions, I think, all have a corresponding instructions. So that should be pretty straightforward as well. Because they should all be binary int operation. Process the thing on the left, process the thing on the right, apply the one uh, uh, atomic operation, not necessarily atomic, but you know what I mean, that performs the thing. So that means I can probably equality, difference, greater, lesser, greater, or equal, less or equal. I can take all of those. Ah, but the type might not be necessarily an int. That's the interesting bit. I think. Because equality, for instance, what matters is only that the types match. They don't have to be the same thing, right? Let's go back to core. Let's look at function expression at the bottom of this file, which is very long. There we go. Equality expression. It's a comparison expression. Compare expect. Okay. What is a comparison expression? That is a other function I have somewhere here. Below, actually. Okay. Wait, what? Oh, there we go. Comparison expression. Okay, that's different. So yes, I check that the types match. They must be of the same type. However, the type could be something at runtime. They could be to structs, for instance. So this is not gonna be necessarily the type of the register of the result will not necessarily be an int. And this is going to be a lot more complicated if it happens to be a struct. So, okay, this is going to be tricky. So, let's start with one of them. Let's comment the other ones out, and we'll introduce helper function for this when we have managed to express the notion of equality. So here I have an expression in my source code, which is A equal to B, basically. And what I have to do is figure out a way to translate are those two things equal to a very basic set of instructions. Oh, wait, actually, maybe I don't. That's the code generation that has to do this. Because depending, like if we target the LLVMIR, what it will emit is just an equal statement, right? For Pete, this will be a lot more complicated. The code generator will have to like look at all of the fields of that thing and decide what it means to compare them for equality. Like if it's a struct, we need to compare them pairwise. Like it's gonna be a very complicated thing to generate. But as far as the IR is concerned, that is purely a this is surely emit an equality statement, because we do have just an equality there. Compare for equality. Yeah. So that means that is a lot easier. There is, however, one difficulty there, which is that we are going to have to figure out the type based on the type of one of those. We are going to need to figure out to translate the type. However, I can do this later, I suppose, because I can do I can change this to being binary operation, and the register of the result okay. I need to be careful here, because not all binary operations will have the same. Maybe I should change the name. It's not any binary operation. It's not a monoid either. Is that a semigroup? Does that technically form a semigroup? Is that two types written the same type? Is that an endomorphism? Nah, it's not. Basic binary operation is good enough for now. And here, the trick of this is the register will have the register type of R1, because it will assume here. Actually, we'll check. Unless register type R1 equals register type R2, or yeah, when different, report ICE. IR lowering. Binary operations. Basic binary operations has incompatible types, incompatible register types. This one is just for comfort, in the sense of, like, that should never happen. And I don't even need to test it. But if it ever happens, I want to detect it. And I'll add 2 strings of information. Left-hand side type will be show of R1. Let's show the entire register. And let's show the entire right-hand side register. That is purely for my peace of mind, just to not make sure that, like, this assumption I'm relying on is actually correct, and I haven't made a mistake using this function. But this should absolutely never happen. Okay, so now process the left-hand side, process the right-hand side, get the type, which is assumed to be the same from any of the 2 registers. The target register will have the same type, and the instruction will be whatever the instruction is given here. So those are all basic operations. I guess I don't even need to handle string concatenation actually now. This will be done as part of the code generation, I suppose. Unless I want to be able, no, I think even if I want to translate my IR into the LLVM1, I can do that by, like, looking at the type of the of the register. So I think I don't need to do, unless I really want to separate that. Yeah, maybe I should leave that to do. Okay. So now this is basic binary operation. So binary int operation becomes basic binary operation. There we go. And now I can do also all of those at the same time because they also become all basic binary operation with their respective instructions, E1, E2. Can remove all of the do blocks. They're not needed. Up. Compare not equal. Compare greater than. Compare less than. Compare greater or equal. Compare less or equal. There we go. So that's those things done. Now we have Boolean and Boolean or. Do I need to implement short circuiting as part of this? I think so. Because I think it would be incorrect for the IR to be compute the value on the left, compute the value on the right. Shit, that becomes an if. Huh. Unless, again, I delegate. No, I can't do that. I cannot do that. Because here I will need to insert all of the register. I will need to do all the register thing. I will need to translate the expression. That expression must only be computed if the first result tells me true. Otherwise, I cannot perform over the translation ahead of time. That would make no sense. So, this is tricky. Okay, so here is where things get very tricky, but this is fine. We've already been through processing an if, so we know how to continue with this. Okay, so we encounter a Boolean and expression with a sub-expression 1 and a sub-expression 2. It is A and B. What the fuck do we do? I am gonna remove this entirely because I need to figure out. I think actually I'm gonna also do something else. I'm gonna remove and an or from this. Well, no, actually, they need to be there. No, they don't. They don't. I can remove them entirely. I'm curious, what does the LLVM IR? What does it do for? I would rather find the basic. There we go. There are no Boolean expressions or something like this. That's not a thing that exists. So yes, I will need to. Yep, okay. If I look at the Boolean type, is it a thing actually? DLVMIR is not my target for this at first, but since I will want to do an export to it because I think it would be interesting, I think it would be good to... Okay, it doesn't even have some notion of Boolean apparently. Okay, so I'm right in the way I approach this. Okay, so we are currently in the current block, but we have encountered a Boolean AND. And a Boolean AND is not an atomic operation because it needs to short circuit. What that means is I will first process the expression E1 that will give me... I should probably E1 to LHS, E2 to RHS. There we go. So here, I process the left-hand side of the Boolean AND, the first part. And after this, I need to treat this as if this were an if block, basically. And this is going to be my first brush with block arguments slash phi functions, because the value of the result will depend on which branch we took. Okay. This is going to be tricky. So, I have added to my current block the computation of the left-hand side of the Boolean thing. I have my Boolean register there. This is where the value is. I will terminate the current block. And the current block will terminate with a branch. If it is true, we will need to go to some kind of to a block for the that will be where we can compute the right-hand side label. If it's false, the result will be false. And I will need to go to the resume label, which is where we're going afterwards, basically. So that means I will need to create the right-hand side label. I will need to create the resume label. I terminate the current branch, the end. I can immediately seal the right-hand side label. I can process the expression of the right-hand side within that new block. That gives me the right-hand side register. There is an issue. There is an issue. There is an issue. I cannot rely on the general purpose phi function detection thing because this is not a named variable. Huh. Oh, this is gonna be tricky. I can do this manually, I guess, but I will have to triple check this. Okay, so. This is incorrect. I am not going to target this label with no argument. I'm going to target with the left-hand side. No, I'm not. Yes, I'm not going to target with anything. But in the off case, in the resume label, I am giving an argument to that block, and that's the left-hand side register. This is where the value that the target, the resume block will need. It is this left-hand side register. Which I guess is a constant false if we ever come from this place, but that's not something that I can express easily that way. Okay. I go to the label for the right-hand side. I only go there if the left-hand side said true. I process the expression within it. And then when that's done and I have the right-hand side register, I terminate the right-hand side block with an unconditional jump to a target, which is the resume label, with an argument, which is the right-hand side register. Okay. 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 Then I will need a new register to contain the result. So the target of this whole thing will be a new register of type Boolean. And I need to append an argument. So append argument I need to append an argument to the resume label. Where do we continue after this? Where do we continue after this? I need to seal the resume label. I need to seal the resume label because I have both of its parents. I need to append the argument of the resume label, and it's the target register, and I need to return the target. There is, however, an issue that I hadn't thought about, which is that all of this code so far was assuming that we resume processing. Like if I have two operands, like an addition, I do the addition on the left-hand side, I do the addition on the right-hand side. We are always in the current block. That is no longer true because of the short-circuiting of Boolean and expressions. An expression can result in branching, can result in blocks being created. And I don't want to have to do threading, so we are going to be adding the current block to the state. This is going to be, however, a lot more dangerous, I suppose. This is where a lot of mistakes could happen. But I think this is nonetheless the only good option that we have. So we're going to have to be careful. So, and there's one downside. So we're back to adding current, which is a label, and that means that when I initialize the thing, I will need to initialize with the current block. Okay. Does that mean that I create the starting block from the start? Probably. One here, and the current block will be, okay, label, it'll just be labeled 0. Okay. Okay. That means there's a few things I can change. I probably, parents like this is fine. I can probably current parents being a thing that gives me the ones for the current thing. So current parents is just parents. It's just current block into parents. I will need to know current block. Which is gonna be a label, which is just gonna be current block is gonna be use ls current. And I will need a way to set the current one. So that's comes get block info. Current block info becomes something that gives me a lowering m of a block, and that's current block info is so that's the lens. So I'm gonna do get block info that for a label gives me a lowering m block, which is gonna be get block info is for a label is use block info of that label. So that's use block info. Current block info is get block info of the current block. Append instruction will always be to the current block. I will never be appending instructions to something that is not the current block. So this is going to be label is the current block. And then the rest is the same. So this doesn't take the label anymore either. This only takes the register. Current block and do that. Set terminator will be the same. And this is probably actually block info in all of those. Block info. Block info. Okay. And I will probably need to add more functions because at some point we're going to need to change the arguments to the terminator. And I can't do that with that at the moment. I guess I could... no, I will need to do it on something that is not the current one. So I think I'm going to change this to terminate. And actually, there we go. Start block label thing start block is gonna be doing a very basic thing, which is ls current equals label end block gets the current block and puts the terminator there. I could make it so that I could make it. Yeah, let's do that. Although it's going to put a bunch of ice in a bunch of places, I'm okay with that. That's a maybe label. There might not be a current block. That way, if I ever try to do If I ever try to do things on the current block when I've terminated a block but not started a new one, or if I'm trying to start a new one without terminating the previous one, internal compiler error immediately. And I probably want to detect those, even though it would be even better if I could use a type system to avoid that, but like, you know. Let's do that. So that means I'm back to 0 here. That's fine. So now this is where getting the current block should always check that there is a current block. Any use of current block should fail if we're not in one. So this is that, and an on nothing m report ice. We found a major compiler error in the IR lowering. Tried to access current access non-existent current block. And I probably don't need a lot of information there. Perfect. So anything in any of this that uses current block will fail. And here, I can do something a bit smarter. Use ls, well, modify ls current. The lens pointing into my state will be modified with the following function. Case nothing. That's perfect. We modify the value to be just the label. Just label. Oh no. Report ice. And I will include in this case previous block. New block. Well, label, let's be explicit. And new label. Okay. And that line is no longer required. We've modified the previous one, and when the value of the previous one is nothing, the new value becomes just a label. There we go. Okay. So now, first I'm gonna have to add a ton of things to the exports there. So set terminator no longer exists. I might put that in a new category. This is gonna be block, I suppose, and I will have start block and end block as to the two things that then exist. Current scope, or a bunch of those. I might need current block actually. I don't know if I need it. I'm gonna try without it. We'll see. Parents still a thing. Current parents even better. Okay. That should be enough for now, so I can go back to everything we've done so far, and I can change everything. So start label, make label, seal block the start label, start block of the start label, which is not the same thing as sealing it, and then I guess process block can start it. No, because process block will continue to go recursively. Oh, no, that's fine. Okay, let me explain. At the moment, process block processes one statement from a block, and when needed, explicitly calls recursively on the next statements of the block with the with like call itself by knowing like okay, this is where we continue on the rest of the statements. This might no longer be required since we now keep track of what is the current block within this. So instead, I might be able to make a function that does a fold over the thing. And I might even try to see if there's a combinator in control monad loops that will help with that. Okay, so this is process statement now. Process statement. And we can actually start making process block. So this will actually be that. This is process block. It contains the block that we're processing and the set of statements that we need to process. Statements. What do we do in this case? We start the block. Yes, this is going to be a lot better. Okay, this is going to be a ton better. We start the block of that label. Then I want some kind of unfold. Let's go at control monad loops. No, that's not exactly what I want. Maybe I want some kind of fold, actually. But I want a fold that is able to... I might have to write it myself. I might have to write it myself. Okay, let's write this recursion myself. Let's go with the statements. And what do? We do a case. If we have arrived at the end of the statements, then that means there is no longer anything to process. This is this block that we can move here. So I look at the current resume label that we're supposed to jump to afterwards. And if it exists, that's perfect. End block, we have arrived at the end. We have arrived at the end. That's good, perfect. So we end block, we're done. We're done with processing the block. Otherwise, we don't find a resume thing that will also be ending the block or reporting an error if the function doesn't have a unit type as its return type. Okay? So that's the case where there is no longer any statement to process in the block. When there is more statements to process, what do? We know where we are and we know the current block. We don't have to do any of that. We process the statement, and that will tell us whether we have ended, whether we can continue. So when this, then go recursively on the rest of the statements, continue processing. We will only return false from this thing when, okay, there might be more statements, but we haven't counted an unconditional jump. We don't need to continue processing. So if we encounter this, if we ended up at the end of the block without encountering an unconditional jump. So this now no longer takes the label, since now it's part of the state, and returns a boolean that indicates whether we can continue. And this, if m is reachable now, can go here. Yeah, I suppose we don't need to process. Like, if we try to start a block and it is unreachable, if we're trying to process a block and it is unreachable, no other block targets that thing, then there is no point there. There's no need to do anything. I will probably need to change my is reachable. No, actually. Yeah, because I don't want to start the block if it's not reachable. Okay, so processing a block is I test whether it is reachable. Okay. I don't want to, how do I do this? Let's do an explicit if then else. That's just better. So, can be reached is this block I'm trying to process reachable? If can be reached, then do start block label and go over the block. Else, that block is not reachable. Unless the block is empty. If it's empty, it's perfectly fine for it to be reachable. But if it contains stuff, so there were instructions there that I was supposed to process, but they can never be reached. This is where I will emit a warning for this code is unreachable. And I will probably want to prune that block out of the list of blocks. So this would be, oh, if I don't have the lens, or do I do that later? Maybe I'll leave that as a to-do for now. Prune block question mark. There we go. In a case where it can be reached, start block label go block. Otherwise, unless it has no instructions, emit a warning and maybe prune it. And the go is the manual recursion over the list of statements. And by the end of this, we might no longer be in the same block, which is perfectly fine. But when we arrive at the end of this, if there wasn't anything, there was no unconditional jump, then if there was no unconditional jump, then we look for one and we might emit an error if there wasn't any found and we can't do anything. And otherwise, while we did not encounter any end, we continue processing statements. Okay, which means now processing statements becomes a lot easier because not only does it not need the current label, which is part of the state, it doesn't need to do the recursion anymore. So process statement is what was this go function before. It's just a case on the statement. So I can do that. The only thing is, I have to go over all of them now. So if I encounter a continue statement, this is still true. If there were, I can't emit this warning anymore. Oh, but I don't have to emit it here. Perfect. So here I can do if m process statement, go recursively on the statements. Otherwise, if I got a false, so something has ended, here is where I can do like, hey, this block has ended because process statement told us that we arrived at something that was an unconditional jump. There is no way for us to continue processing, but there were statements that we did not process. This will require reporting, at the very least, a warning. Okay. So for now, so we get, if we encounter a continue statement, we need to find the current, the where we're jumping by getting the next label from the state, the current continue label. And if we don't find it, we like crash at the moment. We will probably report a proper error at some point if we change something. That's fine. And that means we end the block. Oh, that's even better. I don't even need to return a boolean there. I can check whether I am currently in a block. Because I will always, the only cases where I need to, yeah, okay, so I can change that. That's perfect. So, is within a block is a boolean that will tell me it is just looking at the block, and the function I will apply is just. So now this becomes process the statement. If I'm still in a block, if is within block, then go recursively. Otherwise, do a final check on the stuff. There we go, even better. Okay. So here, I have found a continue statement. this ends the current block because we are jumping unconditionally to something else. I encounter a break statement. This ends the block because we are unconditionally jumping to something else. I encounter a return. I therefore end the block because we unconditionally return out of the function and there is no need to process anything. If I find an expression statement, I simply process the expression and it will in all likelihood leave me in the same thing, but I don't need to explicitly end the block. I delegate to process expression. Let statement, I process the expression, which might put me in a new block, but that's fine. Okay, so the assumption that process expression will always leave me within a block, that there's no way that process expression will make me jump. I think that's fair. I think I don't see any counterexample, but let's keep that in mind. Let's write it down here. Because we might change blocks, but we should always be within a block. Okay, so that's the expression thing. For a, and we don't need, yeah, the register is unused. I suppose process expression might give me some some expressions will not give me any register because some expressions will be an assign that returns a unit and there is therefore no register there. Hello, how are ya? So I think I might need to change process expression to give me a maybe register, which means I am gonna expect, I'm gonna have to check that more checks. That's fine. We'll do that later. So back to here, we encounter an expression, we process it in the current block, and we ignore the register it gives us because by definition, that thing is lost being a top level expression. We process the expression of the let expression. It must give us a register. Aha, and here, yeah, here for now I will need to know the current block. That's fine. However, here I don't necessarily have a register, and I must have a register. Because otherwise it means the thing gave us a unit type, which is not allowed. I think I don't want to handle this kind of like stuff at every call site, so I might introduce a new function around process expression that does this kind of check and always gives me a register and does the handling explicitly once. So there's going to be a force expression, I suppose. It's not just about processing it, it's about forcing a result. Oops. So force expression will take the exact same stuff as this, but will always return a register. And force expression given, I don't need the label, this is now implicit in the state. force expression of some kind of expression is gonna be process expression of that expression. So I can probably do that into a fmap force result, because every single time we're gonna need the thing, we have already, if everything went well, if there is no bug in our code, every single time we're gonna need to have an actual register, it means we need to have something that is typed that is not a unit type. Since we have already done all the type checking, in theory, at this point, the situation where we expect a register and we don't have one should never arise. So, force result can be... Actually, I'm going to write it differently. This is going to be process expression there, and an on nothing m. If there is nothing in there, and we were expecting something, that means somewhere our type checking went wrong. We have emitted an AST that's like an AST that we're trying to lower that's just incorrect. And if that ever happens, report an internal compiler error. We are, as part of the IR lowering, typed expression did unexpected unit type in expression. That's not necessarily correct. Maybe for panic we'll want something. No, because for panic we'll always want to have a register. I haven't thought about panic yet. That's not a good error message, but that will be good enough if it ever happens for me to know where to look. And no additional thing. Okay. I guess I could try. I could actually add as debug information. Let's show the expression that failed to give us a thing. Okay, perfect. So now I can go back to here. A let statement is force expression. I get the register. And I, for now, get the current block because for now I need to do this kind of thing. I need the current block to know. I will probably want to introduce some function that does that for me so I don't have to do a call to current block here, but that's fine for now. And now here is where it gets fun. This if statement will cause us to end the current block and move to a new block. So here, this recursive call doesn't need to happen. So I get the label, I create a label for the new block that will come after. Actually, let's start with the while because the while doesn't have the recursion, so it doesn't have the if here. So here for a while block, I create 3 new labels for 3 new nodes in my control graph. The condition, the loop, and the resume one, which basically map to the condition here, the while header. The loop is this starting one, and the resume is here, the exit. So I end the current block, and I end the current block by jumping unconditionally to the condition label. Which means now I have to start block of the condition label. I force expression of the while expression in this block there, which might end up creating more blocks within this, because that might happen because of short-circuiting and stuff. That's fine. But whatever block we end up at the end of this, I end the block by doing a branch. And I branch to the loop block label if this register is true. I branch to the resume label if it is not. And I do this branch based on this register. Then I am no longer in a block. I seal the loop block label. I start block. I don't even need to start block. That's fine. It's fine. It's fine. It's fine. Because process block will do the start for me. So with a loop scope, which tells me where to go when we fall at the end of the block, we just go back to the condition, and where to go if the condition tells us, if we encounter a break, basically. We process block of the loop block label with the while body. This finishes the block, this starts and this ends it. So at this point, we are no longer in the block. So I seal the condition label, I seal the resume label, and I process the block that is the resume. Well, yeah, process resume. No, I don't process things. I start block resume label. And that statement will have ended the block where we started and started the new block at the end. And the color will be none the wiser. We started in a block, we ended in a block. The fact that there was a bunch of things happening to the graph in the middle will not be seen by the color, and that's fine. Well, not be seen, not will be the same thing for the color. And now we can check the same thing for the if block. So this is going to be somewhat similar, except a bunch of this is going to be at the end. But at the end, I seal the resume label and I start block of the resume label, because the if is going to end the current block. Now, let's go back to here. I add computing the expression of the if to the current block, to the current node in our control flow graph. I create a label for a new block, which is the if block. I get a label for the else block, which, if there is no else, is just the resume label, because this is where we're going to go if in the case where we have the if doesn't, the condition is not true. We end the current block by branching explicitly between either the if block label if this register is true, or the else block label, which could be nothing and just the resume label, if that register is false. Now, we seal the if block label because we have all of its parents already. It's fine. And we process the block, which starts and ends whatever. It starts this block, will end on whatever block there is at the end of the thing. It is fine. But at the end of this, I am no longer in a block. Could I? No, I don't think I can at the type level. I don't think I can at the type level, since I do start blocks and end blocks in the middle of instructions like this. I don't think I can reflect the fact that I'm in a block or no at a type level, which is a bit annoying. Anyway, um, unless I were to like carry a witness explicitly, but that's the whole point of not having the current label, the current block as a witness is as an argument is I don't have to do the threading myself. So the whole point of this is I don't have to thread the block. So yeah, I suppose it's fine. And now in the case where there is an else block, so there is a dedicated else block label, I seal it, and I process the block. And if there is an else if, I process the if. Oh, and this is where it's wrong. Okay. Because here this process block will start and end the else block label. Here, I'm assuming that I'm already in a block. So here, I have to start block of the else block label, process if, and process if always ends up with not being in a block. Because at the end of this, either we call process block and we are not in a block, or like and there's not no else and that's the end, and or there is an else and we do process block, or we do process if, which is a recursion. So we are never in a block at the end. We are done, which means when I come back from this in the if here, I need to seal the resume label, start block of the resume label. Okay. That should be all for the changes we've made. Okay, I'm gonna finish pre-loop block, condition block, loop body block, start new outer block. Okay. Okay, so we can go back to this. Now, all of this current is no longer required. So, a Boolean literal expression, I create a register and I append an instruction to the current block, which is a thing. Okay. Now, all of this still gives me a target, and for now, it needs to all be a Boolean, which will depend on whether the previous instruction gave us a result that needs to be in a register. Every single time we have a register for the target, the answer is yes, hence the thing. So I think I can do a pure target into pure just target. There we go. All basic binary operations are of that shape. We process the expression on the left-hand side, adding its instructions to the current block. We process the expressions on the right-hand side, adding its instructions to the current block, which could end a block, create a new one, that's fine. And I check that the types are matching, it's fine, and then I create the new register that contains the result, and I append an instruction to the current block, which is that. Okay. And now I can go back to the thing that made me do this like half an hour change to everything, which is Boolean AND. There is no Boolean AND instruction in the LLVM IR, and there is not as a result in our IR, because the Boolean AND is short-circuiting. Which means I can't do that. I can't do process expression, add the computation of the left-hand side to the current block, process expression of the right-hand side to the current block, because we need to only perform this when the left-hand side return true. Otherwise, we need to short circuit. So we need to branch So a Boolean expression, this Boolean expression, will have to end the current block in the control flow graph and do a branch. So here, we force, actually, even, I might have to do process expression into force expression on this thing so far. We force the expression on the left-hand side. We can force because this must give us a register because we expect a value out of this. And now we can create two labels. The right-hand side label, which is if we need to compute the right-hand side, and the resume label, which is where we go after either branch. We can end the current block by branching. The block in which we were ends, and we branch. We branch if this register is true, we go to the right-hand side. We must compute the right-hand side of this Boolean expression. If it is false, we go to the resume label, we skip computing the right-hand side. And we give as a block argument the value of the left-hand side register, which we know is always going to be false, but this is just to say, basically, this needs to be on the stack moving forward. Now, we have ended the previous block by setting the branch. We can start processing the next block. The next block is the right-hand side block. We start the block. It can be sealed because we already know all of its parents. So now we have started this one. We force the evaluation of the expression on the right-hand side. That gives us the register in which that value is stored. And regardless of where we ended up, because this expression might also contain things that end a block, start a block, it's fine. Because force expression always leaves us within a block, we can end block whatever block we end up after forcing the expression of the right-hand side. And this block being the if block of whether of the case where the first left-hand side returned true, we always unconditionally jump to a target, which is our resume label, with this argument, the right-hand side register. We are no longer in a block. We are no longer in a block. So we need to start. We seal the resume label because all of its parents are known. We start the block of the resume label. We create the register that will contain the result, which will be given as an argument either by this or by this, the two parents. Or more, actually. Well, no, in this case, only two. I append an argument to the current block, which is this target. As in, this register is not something that is the result of an instruction, it is the argument to this block. And I return this register as being where the result of the previous, of this instruction is stored. And we are now in a new block. Okay. Now let's do Boolean OR. An OR expression with a left-hand side and a right-hand side. We force the expression on the left-hand side. We have a label for the right-hand side, a label for resuming. If the left-hand side is true, we don't need to compute the right-hand side. We can short circuit. So In the true case, we jump directly to resume label with the left-hand side register, which will always contain true, but that's not something we can track at this point. And in the case where it's false, and therefore we don't have enough information, we cannot short circuit, we need to jump to the right-hand side. And then I think everything else is literally the same. Yeah. Okay. Yeah, I think that's the same. Okay. That was a lot of work. And we are not done. So here, I want to have the AST again, because I want to look at my expressions that I am actually translating. I want to have a look at my IR, because this is the expressions I am generating. And now we have something a lot simpler. A cast expression, where I have an expression, E, and I have a type, T. What do I do here? I'm within a block, it's fine. I can get the register. How did I name it when it's only a simple thing? Previous. Okay, so I can do that. There is, however, going to be one difficulty there, but it's fine. So I force the expression of the thing to add a bunch of instructions to my current block. And at the end of this, I get the register saying, okay, the result of this expression is in this register. Now, I will need to get to translate type. Target type will be a translation of the type T into something that can be captured by the IR. And I guess I can just do it like this. The target register will be make of a register with the result of translate type of this type here. And for now, as part of the IR, we don't need to do more. It is enough to just add instruction, append instruction, append instruction, and the instruction that we are appending is a cast where the target is this register, and the value where we read the previous register is this one, and the type that we are targeting is not needed because it is already captured as part of the register. Registers are typed. This is fine for now. As part of the IR, I can keep this very basic cast level thing, because in the LLVM IR, cast is just like a basic operation I can do, and the difficulty will be like what do we do with this will depend on the backend we're targeting. When we're targeting Pete, this will be a no op for a lot of types, but for some types like cast to enum, a bound check will be inserted. So at the code generation time, I'll be adding some kind of like if thing, like, and some kind of branching stuff, but that's part of the code generation that is not done as part of this. So for now, that is just a cast. Although I guess I could make it. I don't want to have to encode the notion of a panic within DIR, because what the LLVMIR does for a panic is going to be very different. Yeah, I think this is fine. Maybe I'll think about adding the branching and stuff for the casts here. I'll leave a note for later. Because maybe it makes more sense to do this as part of like the IR stuff and then translate that into, I don't know. I'll think about it. Okay, so that was the cast. Not too complicated, thankfully. We need, however, to return just the target. I'm almost tempted. I am tempted. I'm gonna do it. Append instruction is gonna give me a maybe register as a return value. And that's going to be based on the instruction. And that's basically, does this register, this instruction have a... Oh, I didn't. Oh yeah, no, of course. Oh, some of them have a list of registers. Oh. Some of them have lists of registers. That is because of an implementation detail of... Nah, I think I'm not gonna put that as part of this thing. This is gonna be up to the code generator to deal with that. Okay, let me explain. The way I deal with references in this language is very, very ad hoc. Since this is purely stack-based language, there's no heap, references are not pointers, there's none of that. So I do a bunch of ad hoc stuff where references are only allowed in function arguments. And it's basically, okay, the function argument can be given in place. And as a result, I expect that that value to be moved to the function, to the argument in the function, and then moved back afterwards. Which is why I have this list of register for invoke things, because I was thinking of translating at the IR level by the arguments to a function also contain the register of the things that are going to be modified in place. But in fact, I think this will be an implementation detail of the code generator. So those are going to be maybe register. Okay. So now here I can do, because some invoke thing, some invoke stuff will not target a register. And some expressions will not. Yeah. Yeah, okay. This is a bit inelegant. This is purely to simplify things. Every time I'm adding an instruction to my list of instructions, I can have a look at, the target and return that. So that I don't have to do it twice, basically. That's the target. That's also the target. That's the target. All of that stuff is irrelevant. All of that stuff is irrelevant. and just target. Except here, for those two things, this might not have a target. Those are a few of the things where an assignment, like all of those things, perform a computation that targets something, puts a value in a register. A function call might not get me a register because a function call could be a unit function call that does not return a value, in which case there is no register. Those things are a maybe. Okay, so now with that done, which is a tiny bit ugly, but not the end of the world, it doesn't encode any difficult behavior. Every time in this function where I do append instruction, I don't have to do pure just target underneath, because this append instruction will return the target properly. So I'm saving a bunch of very verbose and not very useful stuff. Just gonna align this for readability. Okay. Append argument. Wait. Did I make a mistake? No, I did it for append instruction. We're good. So here, I don't do an append instruction as the last thing. I need to actually return it explicitly. Likewise here, append instruction does return the thing. I don't need to be explicit. Append instruction returns the target. I don't need to be explicit. There we go. Okay, so we're done with all of the basic ones. We're done with the literals. We're done with... We've not done anything about references. That's going to be later, I think. If we even need to do anything at all, it might be possible to just not do anything at all. Like, not emit any instruction particularly, and just ignore reference expressions, basically, that were only there for the type checking and stuff. Int negation, that's done. Bool negation, that's done. Addition, subtraction, multiplication, division, modulo, all of this is done. Range, not supported yet. So that's going to be very easy. Those two ones are going to be... Oh, there we go. Unimplemented for now. Convenient. And now we have the assignment stuff. Assignment is interesting. And then we have all of the compound assignment, which should not be too difficult. Famous last word, of course. Let's start with assignment. Wait. I am extremely wrong. Okay. I am extremely wrong in the sense that the left-hand side of an assignment... Oh god, okay. This is gonna be tricky. I'm gonna have to figure out... I'm gonna have to figure out what the shape of the thing on the left-hand side is. Because it is an assignment, sure. But are we assigning something to an array, to a struct field, or are we assigning something to a variable that is in scope? Depending on that, it will not be the same instructions that we're going to generate. So we have the left-hand side, the right-hand side. I am tempted to do a thing, because a lot of them, all the compound assignments will be of the same shape, and I already know the shape. Ah, that's a bit more complicated than I thought, because likewise, let me think about this. Let me think about this for a second. How do we translate a plus equal, a compound assignment, on an int? We are gonna have to do translate the path expression on the left, the x, as something that we retrieve. We get the register that points to this value. Then we compute the right hand side. We get the register that points to it. We insert an addition to get the int that goes there. And then we perform an assignment to the thing on the left hand side. So I suppose oh, this is tricky. Okay, but still I can get the value by doing a force expression of the thing on the right hand side. And with that, I can do an assign left hand side of the value register and always return nothing. There is no register that comes out of an assignment. Where assign is going to be some local helper here, which assign will be unimplemented for now. And I can do a compound assign. And compound assign, given a left-hand side and a right-hand side, will always be the same thing. It will be force the expression on the left-hand side. Why is that the value there? Force the expression on the right-hand side. What is the value there? It will actually be basic binary operation of that instruction, the left-hand side, the right-hand side. I get the register that contains the value, and I do an assign left-hand side value pure nothing, which, yeah, I could consider having the assign do a pure nothing, and I just don't have to do it twice here. Okay, so that compound assign which is okay. We do a basic binary operation by computing the left-hand side, the right-hand side, performing the operation, and then we need to know what kind of assignment this is, which is what the assign function is for. So that means oops. Um, okay. And now we just need to do this is subtract. This is multiply instruction. This is a divide instruction. This is a modulo expression, and this is a exponent expression instruction. There we go. So that's compound assignment done, as long as assignment exists, which we assume is there. Now, assignment is where this gets very, very tricky. What this amounts to is basically I need to figure out what register is targeted by the expression on the left-hand side. If it's just a path, that's fine. I can do a lookup of that register. I know that in this context, X means this register there. Oh, but that's not... That's more complicated than that. If it is a path, if it is a variable or a function argument, then doing an assign creates a new association for that name in scope. So that future, it is not an instruction. It is not an instruction. It is purely saying for the rest of this processing that, okay, we said x equals 4. Well, given the register their value, it means x for future statements will be pointing to that specific register. However, if it is a field, if it's a field expression, then it must be translated to a specific set field thing. Okay, for the purpose of today, I am not going to do assign. I'm going to assume that it already exists. I'm going to do that later because I am close to a point where I can start testing all of this, and I would really like to run some very basic manual tests after streaming for close to 5 hours. So let's finish adding the things that are missing. I am missing only a few expressions. But of course, I am missing the more complicated one that I did not want to have to express today, because that is difficult. I am missing path expression, field access expression, and so on. And this is going to be a matter of adding enough underscores for it to be happy. Field access expression is 2 of them. Call expression is 2 of them. Array expression is 1. Index expression is 2. and struct expression is 2. Okay, so that should be everything for now. That's still, we're lacking, the lack of assignment is kind of a problem because we lack the ability to do anything. We lack assignment and function calls. So the functions we can try to lower into IR are gonna be very, very basic. But we can still try a while loop with a break. We can still try to have a loop with like a hard-coded condition, and like we can still do a few things with this, and we can check that some of the statement logic is working. So let's make this compile first. As current doesn't exist, it's because it is current block. I could just name it ls current, since ls current is not exported anyway. Yeah, it's here up. I can do that. Import Iceland in scope, that means I require import internal ice. There we go. Uses, not use, because I'm applying a function on the thing. So block info given a label gives me traversal. This might be something where the 0.3-ness makes it difficult for it to figure out the type. Aha, there we go. This cannot be a traversal because of a lack of monoid block. How does that make sense? This compiled a layer. So what have I changed? What if I leave this uncommented? What do you suggest there? That's just a lens, I suppose. So without making it explicitly a traversal or anything, maybe... Okay. Set field has 4 arguments. Interesting. Being given 5. Yes, I can't count. Okay. Defined but not used is within block. Get block info. I'm surprised get block info isn't used. Oh yeah, I suppose. I might comment them out for now, since I don't need them for now, to avoid having a bunch of things I don't actually need in the code. So for now, those go away. Current no longer exists, and the block just always ends up and the current block. Current block is not exported out of this. with two R's. Current is no longer required here. Translate type doesn't exist. That's a problem if you want to do tests. That means all tests will have to be, yeah, cast can't be done. Because for now, translate type will be unimplemented. And I'm not even gonna type it. It is anything. Okay, so go block doesn't make sense. Why doesn't it make sense? Because that is a list. Oh, but it's expecting a list of lists? How does that make sense? Because here I have made a mistake. This is no longer taking a block. This is taking a statement. There we go. Couldn't match. Return just a register, I suppose? Oh, actual maybe register. Why is that? Because process expression gives me maybe a register, which makes sense because the expression could be. However, if there is an expression, it must not be unit, so that can be a force. Process if doesn't need. No, what's wrong with this? Process if needs this label that we are gonna process because we're gonna start it. Wait, why do I need current there? I don't think that's correct. So I think, yep, resume label if info. I don't give the current. And within process if, start block, process if resume label. So resume label is always part of this. Wait, do I need the resume label as part of this? I don't, I think. I don't think I do. Because I am operating inside of with inner scope, which means. But it could give me a maybe label. That's annoying. Yeah, no, okay, let's do it this way. Let's pass it explicitly. Let's pass it explicitly, even though it's technically not required because I could get it from the surrounding context. It's fine. It's fine. It's fine. It is fine. Oh, I suppose, yes, those are typed expressions. So, typed expression, and I'm gonna deconstruct it here, and this will be a case of the exp value, I think. Pure nothing. Nothing. No instance for EQ type. Yes, that's correct. Let's fix that. Where are you, type? You're here. You're trivially equal by being a very basic, simple tree of things. Okay. Define but not use. Yeah, that's correct. Assign. Basic assign. Pa-pum. to differentiate with compound sign. Oh, and those are not indented properly. Let's fix that. And I'm just gonna do this for readability. Okay. Okay. We are getting close because we are at the point where we're getting warnings as errors. Yes, because unimplemented. Actually, I'm gonna do unimplemented left-hand side. There we go. Value is unused. Actually, this will give me the register target. That's not true. That's not true. I can't do that. Okay. There might not be a single target register. It's going to depend. Okay, I can do that. This compiles. So now, let's go to our shitty main that doesn't do much. I kind of want to do interface. I kind of want to do a deriving show on this nightmare. That's going to be horrible. But I still want to do that. Okay, so so let's rewrite this. This nonsense does a tiny bit of like resolving dependencies and stuff. But for now, I'm not going to do much. So for now, it parses the AST, it does the analysis, keeping the cache of everything. But since I've broken a few things about incremental compilation, I'm not going to attempt to fix that this evening. So now what we're going to do is here, I'm just going to get the resolved AST. By doing a resolved AST on nothing error aborting. Basically, no need to continue. We failed to go through this phase. If we have an interface, which is this thing, actually, I'm going to do that. And I'm going to do that, which is going to be the simplified AST, because we apply the simplification phase, which for now is not even monadic because it's total. Simplify module of the AST, and I get the simplified AST, which is this interface. For now, I am not going to display anything. I need to do this update of the state for the very basic incremental compilation I used to support and I don't want to break right now, even though this file is a complete nightmare that is purely debugging stuff that will have to be rewritten entirely from scratch at some point. This is this prints the past information out of the stuff. And I think for the purpose of this evening, go away. I'll print none of that stuff. Although there's part of me it's tempting to just like do a print of the interface and just show the entire thing. But we're not going to do that. Instead, instead, given this interface that we have, we are going to do a lower module, and we are going to obtain our IR. So, back to main. Our IR is going to be obtained by doing a lower module, which for now is not monadic, doesn't return an error, doesn't do anything. And that is the AST. I'm giving as an argument. I guess I should say interface. That is the interface. That's the simplified interface. I lower the thing, and now this is going to be a very basic print the IR. So upon success, print the whole thing. Let's compile that. Okay, it seems to be compiling. First try, I'll take it. Ah, no, of course, I spoke too soon. AST not found, it is not called interface. Actually, I could probably just... Nah, it's fine. Okay. Lift IO. Print is in IO, but I'm not currently in IO. The import is not required. That's fine. Defined but not used, indeed. Wait. That's wrong. Yep. There we go. Thank you, compiler, for catching this. Okay. That compiles for real this time. Let's make a test file. I have a very aptly named test3 folder. Let's make test4. No, PR. I still haven't decided how I want to call the what extension I want for the files. PS? Perfectly fine. Incredible naming here. Let's try this. I will want to have only one function called main that returns an int. Oh, postscript. PS is postscript. Okay, we're not going to use PS. Actually, I'm just going to do Rust mode. We'll be fine. There we go. And this function is going to do a return 42. Just that. Let's try this. Okay. Just gonna directly call the thing. I could do a stack run, but I would rather call the binary directly, which means if I'm doing something that doesn't compile, I can still call the old one. Okay, and I'm gonna give it test4 main. Not implemented yet. There we go. So lowering at line 66. What broke? Emit warning unreachable code. That is an error. Yes, I see the problem. I test, the very first thing I test is whether the block I am trying to process has parents, and therefore if it can be reached. The idea being, oh, I'm trying to process a block but it can't be reached. What's the point in doing this? This block can be removed entirely. Perhaps I should not do that, because the problem here is the starting block, the very first block of the function, doesn't have parents, and therefore I try to process a function, I try to process the block, and I immediately, like, oh, there's some instructions left to process, and this thing is not reachable. So maybe instead, I still think I want, like, the question is basically, do I prune unreachable blocks as part of this, or do I process all the blocks and then be like, some of them are not reachable, I might as well ignore them? I think I want to do, since I'm doing some of the control flow analysis as part of this phase, I think I want to do the pruning there. That means, however, that I need to figure out a way. I need to figure out a way for the first block to be labeled as reachable. And there is a trivial solution that I don't like, but we are gonna go with that for this evening. Which is that I know that the first label in a function will always be 0. And I can use that. That's kind of ugly. I don't like it. That's the easiest solution for now, for sure. But I don't like it. That being said, well, no, okay. I was gonna say, as long as all of the logic that dictates that label 0 is the start label is entirely contained within this module, that's fine. It is not, however, because we start processing a function by doing start label gives me the make label, basically. Which means maybe I should do that and have start label be a thing that is exposed, which means next label is always 1, make label is like there, and start label is something that is always available to the rest of the code, which is the label 0. That way, here I am relying on start label existing, which is fine. And here, if I say, well, okay, is it reachable? Label 0 equals true, and otherwise do that. This thing is always hard-coded as part of this. The rest of the code only knows that start label exists, but doesn't know more than that. So the ugliness is contained within this module. I am okay with that. The implementation detail of the start label being labeled as reachable despite not having any parents is entirely contained within this and doesn't make us any assumptions about the rest of the code. Okay. Internal compiler error. Woo! While attempting to IR lowering. Great grammar there. Try to start a new block without finishing the previous one. So previous label 0 and new label 0. Okay. So what happened? Because we start with no current block. And that means I called start block with something already in the label. So if I start, I did that with the very first block. So yeah, okay, of course. I did start block and then process block. Process block starts the block for me. That's the mistake. Okay. Do I want to do a very quick printy printer for this just to... Yeah, I kind of want to do that. So this is going to be for each thing in the IR, which is going to be a function. Do I have the function name? I don't. Oh, I'm an idiot. I have it from this. I will need to traverse with key then. I guess this is going to be a sequence. This is a traverse with key, I think, simply. No, I'm looking for hash map strict. Does it have a traverse with key? It does. There we go. So here's a function and hash map and gives me a thing. Perfect. That's what I want. So I will want to do a traverse with key print function of the IR. And I want to ignore that result. I'm going to void it. Print function will take an IR function and will perform. Actually, lift IO, and that entirely in IO. I don't need the other state. This is going to perform an IO action. And what we are going to do in this, we're going to take a function as argument. We're going to take the name, actually, which is going to be an identifier? No. Yeah, it's a name. And a function. And we are going to do a name. A name is going to be... I probably want to do a render name that gives me, from a name, gives me a string. Render name is going to be... I don't need to put that on multi-lines. Likewise, I don't need that here. This is throwaway code anyway, but it's fine. A name is, if I remember correctly, a path and type parameters. Oh, render name. Do I have already a render name function in this? I do. Perfect. So text.unpack of show name, because I'm printing strings there, it's fine. Plus this, basically. At the end of this nonsense, we're going to just print a closing bracket. And then that function will be a bunch of blocks. I need to always start with the very first one, so I need to always guarantee. So I'm gonna need to do a thing. I don't have a guarantee that's gonna be in order. That's annoying. Actually, do I want to? Because technically, I don't need. Yeah, in fact, I don't need them to be in any order as far as my code generation is concerned. I think for today it's fine to not do that. So I'm just gonna do for each, I'm gonna do a map, a void of a map traverse with key of print block of the fun blocks. And the function captures the start label, which might not be required unless maybe the optimizer will actually remove some stuff. Maybe I want to keep this. Okay. And printing a block with the name of the label, which is just a label there. And a block is going to be takes a label, takes an IR label, IR function, IR block. I'm gonna need to actually import presentation IR as IR. And what do we do here? For a block, we print for a block, we are gonna print show or two spaces plus show of the label plus open parenthesis plus show of the arguments plus close parenthesis. And then for each block instruction, for each block instructions, we are gonna do a case of, do I just, no, I don't even need to do a case. I'm just gonna do very something. I'm just gonna do a traverse, no, instruction. I'm gonna do a put string of a extremely basic. I'm not gonna try to render anything complicated this evening. Show the instruction. That's perfectly fine. And at the end, print show of the block terminator. Yeah, not show, render name. Okay, there we go. So, okay. Oh, I suppose I can just, yeah. The function main is translated as being just a label 0, which is where we start, there is one assign, which assigns to a register 0 the value 42, and then we return, which is a unconditional jump at the end of this block, and the... Is that correct? That's not correct. That is wrong. Why are we returning nothing there? So, this append instruction, it's an assign integer that assigns to this target. Append instruction is in the lowering monad. It's there. So this should be returning just target, okay? Okay, so why didn't it do that? Because here I encountered a return statement. Oh, maybe... No. Oh, I suppose I must have a mistake where this did return something. I did end block the return thing, and this end block somehow still happened afterwards? Like, is within block did not... Maybe there's a bug in... Yeah, there is a bug. There is a obvious bug. I don't need the trace show M. It's fine. End block doesn't update the ls current. That is a bit of a problem for something that I rely on everywhere for this. So I get the current block. I put the terminator on the thing. I register the parent for the next block based on that. And finally, ls current is set to nothing. So now, if this works, we should be not implemented yet. Line 79. I guess, yeah. What I want to do is when not null statements unimplemented. It is fine to be in the other case. Function main has only one label. The only one element, like atomic instruction in the AR is an assign, integer. The register is the register 0 of this function. It's an int. We associate 42. And what the function returns is like a basic unconditional return using the value in register type, this thing. Okay, that works. Now, let's try to do something a bit more interesting. Let's go back to my file here. Let's do a function foo that takes a boolean. It takes two booleans. I haven't done lookups yet. I can't do that. I cannot do that. I can't do that. That's annoying. So I can't do that yet because I'm gonna get it unimplemented yet. but I can at the very least try if false, return 42, else while true, continue. If true, continue. Okay, that's nonsense, but that should not require anything we haven't tried yet. Oh, haha, it's going to... It's not going to detect the infinite loop, so it's going to complain about the fact, and it's going to crash as a result, because at the end of this else block... No, because there is no... It should be fine. Since there is no way to reach after this while true because all of the branches... Now, because... haha, yeah, okay. There we go. Now if I do that... Now if I do that... Now, because it can still be reached from there... the optimizer does not kick in, so there is a block after this, so it will realize that there is a branch of this function that doesn't have a return, and it will try to signal that there is a mistake, and I think at this point I don't have a way to signal that, or it will crash. So I'm just gonna avoid this altogether with a return 0 here. However, it should not complain about the lack of a return here, because the block after this if else is unreachable because neither of them go to it, therefore it should not be processed. Okay, so this function foo starts at a label 0. We assign a boolean false to a register 0. We branch based on the register 0 of type boolean, and if true, we are going to label 2, and otherwise, we're going to label 3. Let's look at the true, which is this one. That's label 2. Label 1 is written nothing, and I guess it's the unreachable one? Probably. It is probably the unreachable one. Now, label 2 is the one we jump to in the case where something is true. We assign an integer to the register, register 1, and we put the value 42, and we have an unconditional return out of the function using that register. Okay? I'm tempted to just, for the sake of readability, give me 1 second. Wrong main. Render register. Takes an IR register and gives a string, and the register is gonna be case of the register type. It's gonna be type prefix plus show register index, and where the type prefix is a case of the register type of, and we go back to the IR to look at the registers, and type, and I'm not gonna handle anything that is too complicated for this evening because I don't need to handle function types or anything of that nature. We only need to handle those 3, and maybe not even those 3. So that's I, that's B, and that's C, and anything else is undefined. There we go. Which means there's a few places where I'm gonna do a show of. This is gonna be instead an intercalate comma of map render register of the block arguments, and where else do I render? No, okay. I'm just gonna do a show like this, and I'm just gonna move this as an extremely temporary thing. Where are you, register? This is an instance of show for a register where show of a register is this nonsense. I'm just going to do it as let type prefix equal that. In that. Okay. And now we should be back to looking at something a tiny bit more readable when this compiles. Go. Okay. So this nonsense here, we start at label 0. We assign false to a register called B0. We branch based on the value of B0. If it is true, we are going to label 2. If it is false, we're going to label 3. If we jump to label 2, we assign 42 to the register I1, and we return out of the function with that register as the value. If the value of the branch was false, which is going to be the case here, the optimizer will be able to realize this. We jump to label 3, which is this one, and 3 is an unconditional jump to label 4, so the optimizer will be able to realize that label 3 is useless and replace all mentions of the label 3 by label 4, but we haven't started the optimizer yet, because the very first thing we do here is do a while. So the very first thing we do is go to the condition block of this while, which is label 4. Here we perform the computation of the expression of the while, which is this assigned to register B2. Then we branch on the while. As long as B2 is true, we go to label 5, otherwise we go to label 6. So 5 will be the loop, 6 will be after the while. 5 is the loop. Within the loop, we are... Oh, maybe I will... No, I'll need to know the labels ahead of time. Okay, so that just means it's a tiny bit jumbled there. Maybe the optimizer can also sort... maybe the code generator can sort the labels to see if there's ways to remove unnecessary jumps, basically. So in label 5, which is the loop, we assign B3, which is a new register that are true. Register allocation will be part of the code generation. So for now, each new value is a new register because this is a static single assignment form of the IR. We then branch on that B3, which is the if there. In the case where we have true, that is label 8, which is the block there. And in the case we don't, it goes after, it goes to 7, which is it goes to 7, which is the after the if. 6 was so 4 was the while, so 6 is after the while. So if the while condition has failed, we go to 6, where we assign 0 to the register I4 and we return that because the function returns. 7 is the body of the if of the while true, and it is an unconditional jump to continue, so it should just jump back to 4. That is correct. And if we exit the if, we reach the end of the while loop, we arrive here, which if this were empty, this would be, I'll take a second. So 8, which is after the loop, just jumps back to 4 because we are after the if, we jump back to the condition there. If I remove this, 7 should instead jump to 8. The if block is empty, and therefore we should resume immediately to 8. Huh. So maybe I'm wrong about something. Yes, I'm wrong about the order of things. 8 is the block of the if, and 7 is the after the loop thing. So in the case of 8, now which is the if, we jump to after the loop because the if block is empty. We jump after the if, and then at the end of the if, we loop back. And if I put this back, in the if block, we jump back, we continue, and after the while, we continue. Okay, that seems to be working pretty well so far. The fact that we don't have any of the register reading nor any of the variables or anything means that I can't try anything a bit more interesting, but we already have basically like our function is decomposed into a bunch of labels, which are all basic operation, assigns and stuff. And at the end of them, at the end of every block is a jump, either an unconditional jump here, a branch based on the value of a register, or a return. And the control flow analysis worked because it did not complain about the lack of a return here, because both the if and the else branch do contain a return. And if I put a return here, it should crash. It doesn't. Why doesn't it crash? Oh, it doesn't because the block is unreachable. Yes, okay. Well, no, it should reach this. It should reach this. Because the block cannot be reached. The block cannot be reached, and the instructions are not empty. Oh, this is not the block. This is not. Aha. That is a bug. Perfect. So, my mistake is to only check the reachability of where I am. Yes. So here. Okay, I think I understand. Let me just check something. Let me go back to this. The return 1 here should be one of the earlier blocks. If I remove it, oh yeah, here label 1, there's nothing in it because it is unreachable and therefore should just not be, it should be pruned out of this. if I add this, the return 1, then here it is as being assign I5 1 and return just that. So it is there. However, it should have been detected as unreachable, and it did not. And the reason why is the test to see am I in an unreachable block is only performed at the beginning of the processing of a block. However, after processing a statement, I could be in a new block. So in fact, this should be performed but the point is to avoid doing the start block thing here. I don't have a choice then. So the idea is to never start a block that is unreachable. However, every time I process a statement, I could be... Okay, so I think what I'm going to do is I'm going to remove this. And instead, I'll do some pruning later. As in for every block at the end that contains... Because the problem is... No, okay. I can never be in... Okay, no, I can do this here. After I process one statement, there are three possible cases. One is I am no longer in a block because I processed an unconditional jump. That is this thing. And basically, if I'm within the block, I can do things. Otherwise, I am at the end. And if there are some statements that are unreachable, I should emit a warning, which I don't at the moment. This will crash. The second possibility is I am now within the block that is unreachable, and I should detect that here. So let's rewrite this. In a block is the result of querying is within block. Reachable is the result of querying is reachable. Do I have an alias for currently reachable or something? Currently reachable is a is reachable of current block is reachable. Okay. In a block, reachable. If not in a block, do this. when not reachable, do this. Which for now is the same thing. There are statements to process, and I am currently in something. Either my block has ended and those statements are lost, or I have statements in a block that cannot be reached. But there might be I might do something different in the case of I am in a block that is not reachable, which means, yeah, I will need to do something here that is different. I need to end block with a panic, because every block needs to end. It will be prune, probably. I might just prune at some point, but like at the very least, I need to set my context of like I am no longer in the block. Because I was, and I must not be, for this to return. Because at the end of this recursion, I am supposed to be out. And otherwise, if I am in a block that is reachable, then I can go recursively. Actually, I'm just going to name it is reachable, and I'm going to change that to be is reachable is current block. It's that basically into a case. And the case is that. And I don't need the parentheses here. And there we go. What time is it? Oh, it's late. Oh, I've been at this for 6 hours. Oops. And now this. Oh, no, internet compiler error. That is not the error I was expecting. Great. Aha, yes. Yes, I know. I know where it is. Here I'm trying to see, am I in a block? And then I try to see, am I reachable? Which only works if I am in a block, which, you know, I've just said. So here, this should be instead. I assume I have a way for errors to be short-circuiting. But this is going to be a warning. This is going to be a warning. So So let's just write this the boring way. If in a block, then do reachable is reachable, and if reachable, then do go statements. Yeah, I could try to do short-circuiting on booleans, but I want to do something slightly different whether I'm in a block or not, so I'm going to have to do it this way. Else do, this is the case where I am in the block but it is not reachable. Do that. Here, this else is the case where I am not in a block. Check that there is nothing wrong here. It might be fine. Okay. And now I should get an unimplemented error. Not implemented yet. And if I go here and I remove this, I don't have any unreachable code. There we go. Okay. So the logic of the label generation and the register generation, all of this seems to be working. We are generating an IR that we could feasibly at this point export into some very uninteresting LLVM But now the next step will be to make use of the registers. As in, oh, this expression makes use of a variable A. What is that variable A? Where is it coming from? We must do a lookup in the different blocks. Is it part of this block? Is it part of the parent block? And so on. Okay. But we will do that next time. This was supposed to be a short stream to finish what I had started, quote unquote, yesterday. And I ended up working for 6 hours. Yeah, well, I'm back in 18 hours, I suppose, to try to go back to what we're missing, which is finishing processing all of those expressions that I don't process yet, and make sure that we also do the translate type, and then figure out a way to do assignment. And then when we're there, we might have a first pass of the IR lowering by tomorrow evening. After months spent on the analysis, we might be able to get the most basic version of the IR in a week. That would be very nice. Because if that's the case, next week we can try code generation. And it doesn't have to be, half the features of the language are not supported yet. But we could be at a point where next week that makes an image. That'd be nice. Maybe let's not promise that. I can't promise that next week we'll be there, but we're making so much more progress on the IR lowering than I thought we would, just because the analysis was such a slog to go through. Well, we'll see how much more we accomplish tomorrow evening. Thank you everyone for tuning in. Sorry this stream that was a bit less structured than usual, but yeah, I'll see you all tomorrow.